Hello and welcome to the Algebra 1 Spring Final Exam Review video. These are the 5 general topics that will be covered. Quadratic functions, those things with x squared in them. Exponential functions, those things raised to the x power. Systems of linear equations where you do like elimination method and that kind of stuff. You have multiple equations and solving them. Linear inequalities, there's that kind of thing and stuff. And sequences, where we use this format here, t sub n equals blah, 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 blah. All those different things are going to be covered. And guess what? There will be 52 total questions, which really just means one thing, and please be forgiving of it. This is going to be a long video. Now, if you already know the answers to most of the things you're doing and you understand it, feel free to just find the problems that you just had trouble with. If you go here down below, if you're not in full screen, you will see a description section here on YouTube. You will see every single problem number and a timestamp associated with it. Now, if you're on a computer, you can click on that timestamp and it'll bring you right to that. If you're on your phone, I think you have to drag yourself to it. So that takes a moment. But you can still get there, and it's just there to help you out. These problems are in numerical order from the review packet that you have, so they're not necessarily like we do quadratics first, though I do think the first problems are quadratic. And I will just mosey along. So kick back, relax, and enjoy your flight. Problem numbers 1 and 2, we are going to solve these equations by a process that's called completing the square. Now, completing the square is a specific form of factoring a trinomial which has an equal base length and height length. So much so that when you factor it down, instead of looking like 2 parentheses like this, you can actually instead make it look like this squared. And when it comes to solving a problem, this is huge because we can do some square root stuff business after that. I'll be sure to do that with you right in a moment here. So what we're going to do is with this equation, let's solve by completing the square. Now, completing the square involves taking your x terms, your x squared and your linear right here, and finding a constant that will associate with these two sets here. Negative 42 may be the number. I happen to know that it's not. In fact, your number shouldn't be negative here. It's only going to be a positive one. So if this is not the number that's going to help us, then let's get it out of our way. Let's add 42 to both sides of the equation so it's completely on the other side, just out of our hair. So I have x squared minus 4x on this side. Negative 10 plus 42 is 32. I have that on this side. And what we're going to do is the completing the square method involves adding a specific number here that will make it factorable to a perfect square trinomial. By trinomial, I mean a 3-termed polynomial right here. So what is that number? Well, you take your linear coefficient, negative 4, you divide it by 2, and that number is negative 2, and then you square that number. Negative 2, quantity squared, is a positive 4. Remember, it's not a negative 4, it's a positive 4. So plus 4. Now, whatever I do to one side, I must do to the other. That's the form of balance. Okay. Now, I won't get too deep onto why completing the square is what it is. I'll just say if you've dealt with algebra tiles, or if you've seen the idea of what a picture of a square looks like, then I think you get the idea of the dividing by 2 part, probably the squared part as well. The whole purpose of this, once again, though, was to get this inside this guy here. This factors into x minus 2 quantity squared. Now, how do I know that? In a 1x squared quadratic, we're looking for what 2 numbers multiply to positive 4 and add to negative 4. And guess what? It's the same number twice. And you know what else? I stole that from SpongeBob. You know what else? It's going to be this number right here. The number that we divide by 2 down to its sign will actually be this squared guy right there. So do you have to write that stuff? No, but you can use it. Now 32 plus 4 is 36. Now normally when we factor some trinomial into something, we normally want this thing to be set equal to 0 because we want to use zero product property. Well, that would be true if you had 2 different quantities, 2 different sets of values, which we'll be doing zero product property later. This would have to be set equal to 0. In completing the square, it can equal, whatever number we want it to equal. It doesn't have to be 0 because some number times itself is 36. We know it's the same number twice. So our process we get to do to start to get x by itself here is square root. You take the square root of both sides, because the square root of some quantity squared is just that quantity itself. Sort of, actually. The next step really is absolute value, and let me tell you a little bit about that here. The square root of 36 is 6, and what we had to ask ourselves before wasn't just that question. The question was, what number do we square to get 36? Well, it's going to be the same answer as whatever number we plug in here, as whatever number we take the absolute value of to get 6. The reason why is because no matter what you square in here, either positive or negative, the sign will end up being positive. So there could be a negative answer that exists here. Likewise, no matter what you put inside this absolute value, its result will be positive. So really, here's an in-between step that's not written all the time. In fact, I'm probably not going to write it very much after this. The step that's written after this, though, is if you take the absolute value of some number to get 6, that number was either a positive 6 or a negative 6. So you might write it like this plus or minus 6. And for a moment, I'm just going to write it like this because some of your answers will appear in this form. Now, if I'm going to get x by itself, there's still a 2 that's being subtracted from it. So I'm going to go ahead and add 2 over to both sides here. And I'll first write my final result here as x equals positive 2 plus or minus 6. Now 2 plus 6 and 2 minus 6 can simplify even farther, so I'm going to go ahead and do that. X can either equal 2 plus 6 or x can equal 2 minus 6. Now 2 plus 6 is 8 or 2 minus 6 is negative 4. These are your two answers to the original question here. What values of x do I substitute here in order to get negative 10 on the left and right? So there are two different options, and it's kind of strange that you have two solutions for that. You're like, wait, why isn't it just one? Quadratics have this knack of sometimes getting two solutions. Sometimes one, sometimes none. But you might get two solutions because of squaring it. It changes its... I can't explain too much about that. But these are your answers. You can go ahead and double check them. They'll both work. So there we are. That's number 1. Number 2, let's solve for k. K squared plus 8k minus 93 equals negative 9. Okay, same process as last time. We're going to get these two together and complete a square with them by adding a certain new constant value. Negative 93 apparently won't fit the bill, and even if it did, let's move it over for better be safe than sorry. We're going to have k squared plus 8k here. Then plus some other value. Figure out what that is in one moment. Negative 9 plus 93 is 82. 84. 84. I don't need to erase anything. So that's a positive 84 right there. Whatever we add to one side, we must add to the other. Okay. K squared plus 8k plus blank. We're going to take this negative 8. Follow with me because this time I won't draw it here. Divide it by 2. Okay, 8 divided by 2 is 4. 4 squared, that is 16. So this number here is going to be 16. This number here is going to be 16. Awesome. Okay. 84 plus 16 is 100. The question on the left side, however, is what two numbers do I multiply to get 16 and add to get 8? And remember, it's the same two numbers twice. And you know what else? It's the number that we got after we divided 8 by 2. That's a 4. 4 times 4 is 16. 4 plus 4 is 8. This is k plus 4 times k plus 4. Or k plus 4 quantity squared. In order to solve for k here, we're going to take the square root of both sides. And much like last time, the square root of a quantity squared apparently would also be the absolute value of that set. But let's go and skip this step right here. If you do understand that this just leaves you with k plus 4, and the right side you're left with plus or minus 10. That's the square root of 100. So k plus 4 is positive 10, or k plus 4 is negative 10. That's kind of what we're looking at. Subtract 4 from both sides, we get k equals negative 4 plus or minus 10. Excuse me, before I said 4 plus 10 or 4 minus 10, I actually meant right there, negative 4 plus 10. We can simplify this farther. Let's go ahead and split this up. K either equals negative 4 plus 10, which is 6, or k equals negative 4 minus 10, which is negative 14. So two solutions there. Awesome. Solve both of them by completing the square. Pretty nifty process. You know, for the most part, you know, like when it comes to a test, you can kind of choose your own process that you want to do. If it's factorable, you might want to look to factor, and if you do, make sure you move everything to the left side of the equation and set it equal to 0 for the reason I mentioned on this left side here, on the left problem. But for completing the square, if you're going to do it, it's most often recommend that you do it when this k value, the k squared value is 1, and when the k coefficient is an even number. Because otherwise here, if you divide by 2 on an odd number, you're left with fraction stuff. And that's not to say answers can't be fractions. It's just that when you're dealing with a fraction from the beginning and computing it the entire way, you know, it can lead to some trouble. All right, so there's 1 and 2. Number 3 and 4, solve each system by elimination. Okay, the elimination method is a method where you add the same thing to the left and right side of an equation, much like over here. I added 93 to both sides of this equation. And in this particular case, let me just do this because it's going to work right now. Let's say I added -6 to this side and -6 to this side. Well, 6 minus 6 is 0. And 3x minus 6y minus 6 would be this right here. But instead of writing that, instead of doing, let's subtract 6 from both sides, how about let's subtract 6 from this side, and let's add this -3x minus y to this side. Now, am I allowed to do that? As long as they're both the same thing. Because these are equal, I can do this to this side and this to that side, and what happens is I get to combine like terms. 3x minus 3x happens to be 0. I'm just going to go ahead and cross those things out. -6y minus y is -7y. So I added down these lists here, and I happen to eliminate one of my terms. This doesn't always happen so cleanly. You'd have to make sure that your variables are lined up. You'd have to make sure that you have what are called additive inverses. I expect that I'm going to be running into problem sets where we'll solve by elimination, and we don't have this set up, and we'll do those later. But this one is set up, it's really set up for elimination. You can really solve easily. Now, -7 times y equals 0. You know, in my particular class, I've had times where people say, you know, no solution or can't divide by 0, whatever else. You're not. You're dividing by -7. And if you really don't know what you're necessarily dividing by, ask yourself, -7 times what number is 0? That's what you're trying to answer. That question, or that answer to that question is 0. Y equals 0. Now, we're not done with this problem for 2 reasons. Number 1, we only solved one variable, not the other. And number 2, expect your answers to appear as ordered pairs. What we're really finding is what xy value works for both equations, but also if these 2 equations were graphed, what is their point of intersection? And that's really what we're trying to find here. So let me also find the x value that associates with this y value that happens to mark the height of the point of intersection of these 2 lines. So I'm going to take this y value equals 0 and substitute it in for y. How about in the top equation here? You can use either equation. In fact, for some of you, it's recommended that you try both to ensure that your math was right. Let me substitute 0. But I'll just do one of them, and at least for now, trust that I'm doing the correct stuff. 6 times 0 is 0, so 3x equals 6. Divide by 3, you'll get x equals 2. Or when you get your final answer, just make sure, double check in both equations that it actually does work. I'll do this with you just this once. 2 times 3 is 6, minus 0 equals 6. That's true. -3 times 2 equals -6, minus 0 equals -6. That's also true. So your final answer to this is 2, 0. That is the point of intersection where these 2 equations, if they were graphed, would intersect. And I think we solve by graphing here in just a moment. Okay, number 4. Same deal, solve by elimination. Now, as these things are lined up, and by lined up I mean x's with x's, y's with y's, sort of, constants with constants, and equal sign with equal sign, then it is permitted, it is okay to add these down because they're on the proper side of the equation and you have proper balance. As long as I have what are called additive inverses, items that cancel, then it's completely okay for us to use this elimination process because the whole end goal is to make a variable eliminate. 2y minus y is y. This is really set up for us. 18 minus 7 is 1. This problem is going to come by pretty quickly. I already solved for y just by adding these things down. Now substitute it somewhere to solve for x. I'll go ahead and do the bottom equation this time, the original bottom equation there. All right, so we just got to solve for x here. 4x minus y, which is 1, equals negative 17. By the way, I'm going to get in a strong habit of always using parentheses anytime I substitute, just to really reinforce when it is we multiply, when it is that negatives come into play, especially with the quadratic formula. I'll be sure to do a lot of that. And if it helps, I'll write the cleaned up step, which means get it out of its parentheses, because the parentheses affected this value none. If I want to solve for x, first I got to begin by adding 1 to both sides of this equation. I'll get 4x equals 16, negative 16, excuse me. And then divide by 4, negative 16 divided by 4 is negative 4. And whenever I mention be carefuls, be careful, be careful, be careful, I've taught these classes quite a bit, and I've graded exams quite a bit to know when negatives get lost in the shuffle, such as negative 16 divided by 4. If you say it's 4, see, that becomes an issue. Just like I said, negative 17 plus 1 is 16. That is not the case. It is indeed negative 16. Negative 4 for x, 1 for y. This is the point of intersection of those two. Problem's right there. Solving system by elimination. Okay, now we got a little bit more to work with here. Okay, the last two times I said as long as these things are lined up, you are permitted to add down the lines, in which case I can here. Negative 14 plus 7x is negative 7x. 10 minus 7y is positive 3y. And 2 plus 7 is 9. Now, when I added down these things, compared to what I did last time, I was able to actually eliminate variables, in which case I eliminated both of these x's. This step actually did not help me eliminate these variables, at least not entirely. Now, I'll tell you two things with this. Number one, you created a new equation that should have the same solution set as these two. So if you'd like to use this equation, by all means, please do so. And you know what? It would actually be kind of okay to use this equation, because if I lined up the bottom equation, meaning the this one here, with the blue equation right there, I actually now do have additive inverses of 7x and negative 7x. So I very much could solve for this that way. However, this might have just been extreme coincidence that this happened. I wouldn't trust that this would fall into play all the time, or that this is a way that you'd actually approach this problem. But it is allowed, and it is okay. So, but no, I'm going to do this a different way here. I'm going to take a look at these equations here. There are a lot of things I can do with these equations. I will suggest some for sure. I'll tell you one that everyone would look to do, really, is look for a variable to eliminate by finding out which ones you can make additive inverses of each other for very easily. Additive inverses are two numbers that you add together to get 0. 3x plus negative 3x is 0. Negative 4x plus 4x is 0. Basically numbers with the same number, with the same value, but opposite signs. Well, 7, if I multiplied 7 by 2, I would get positive 14. And that could line up with this negative 14 very well. So I could do that. As long as I do with the same thing to this entire equation, I could just double all of these things. And instead, this would say 14x minus 14y equals 14. Crazy, right? So I would line these two up, and these could cancel. Totally okay to do. Nothing wrong with it. It's probably the go-to that most people would do. Sometimes the numbers get rather large. And in fact, if they do, if you're calculatorless, if you don't trust the numbers that you got, whatever else, also take a look at what you can sometimes do here. Did you realize that the top equation could actually divide by 2 without threat of a fraction? What if I divide everything by 2 here? Now this becomes negative 7x. This becomes 5y, and this becomes 1. Now I have additive inverses here and here, and the numbers are just a wee bit smaller. That might help you a little bit. Furthermore, which this one wouldn't seem to help me as much, these could all divide by 7. So you just have x minus y equals 1, right? So you can manipulate these a lot. And, you know, like, why would this help me? Maybe I want to eliminate y by multiplying this all by 10 afterwards. So I get a negative 10y. Anyway, I'm opening your eyes to a lot of options that you can do so you can solve for all of them. I'll go and do the dividing by 2 one to really reinforce that it's allowed. Even if you tried it another way, totally okay. like I said, most people would more likely multiply this bottom equation by 2 to line that up if they catch it. Divided by 2 plus 5y equals 1. Don't forget to divide this one by 2 as well. You know, again, the mistake that's made quite often is that that's forgotten. All right, 7x minus 7x is 0. Remember, I'm adding down these things, adding a 7 with a negative 7. Negative 7y plus 5y is negative 2y. 7 plus 1 is 8. Negative 2y equals 8. Divide by negative 2, right? Not a positive 2. We want positive y equals. 8 divided by negative 2 is negative 4. So your y value, once again, is negative 4 from eliminating x. Now, to solve for y, you have two options here. And, to solve for x, you have two options. One way is do what I did last time, substitute a value of y into either equation or both. Another way is to actually eliminate y next, if you want to keep exercising elimination. I'll just do the substitution for now. You know, this video already is going to be extremely long. Might as well find ways to consolidate it. Where do you want to plug in y? Totally your choice. I'll do the bottom equation. Why not? 7x minus 7 times, check out parentheses, negative 4 equals 7. 7x, this is plus 28, equals 7. Subtract 28 from both sides. You'll get 7 times x equals negative 21, and x equals negative 3. I want to forewarn you, I have not gone through these problems myself yet. So I don't know if I ever expect any fraction answers. If I run into any, there is a possibility of a careless mistake, in which case I'll run through my solution set again and see if I did anything wrong. But if we get fraction answers, hey, we get fraction answers and we'll deal with them, right? Fractions are a big part of math, and don't think that they'll ever be removed from the math that you do. In fact, the more math you do, the more fractions you'll probably have. Okay, number 6. Going back to that notion of what we said last time here, look to see if you have additive inverses from the onset. Apparently we don't. You might already see something a little strange with this problem, because I kind of do too. Then you say, okay, well, let's create additive inverses. Create a variable, or decide which variable you'd like to eliminate. Multiply or divide by something from at least one equation, if not the other, to actually eliminate, and then solve for the other. So maybe you say, well, 5 times 2 is 10, so if I multiply this bottom by 2, actually by negative 2, then, then I can eliminate my y's. Now, why did I say negative 2? Because we're all about additive inverses. I want a positive 10y here so I can cancel. So here, 7x times negative 2 is negative 14x. Negative 5y times negative 2 is positive 10y. And negative 5 times positive 5 times negative 2 is negative 10. So get this out of the way. I'm going to be adding this one with this one. By the way, I could have totally divided the top one by 2 or by negative 2. Just showing you big numbers work as well when we do this. 14x minus 14x is cancels. Negative 10y minus or plus 10y cancels. 10 minus 10 cancels. What? Did that just happen? What? Do the equals cancel? No, you still write the equal sign. Well, what's left here? What does canceling mean? Canceling means becomes 0, at least in this case. Additive inverses becomes 0. I have 0 on this side. I have 0 on this side. And still, you're sitting there thinking, okay, did I break this problem? Did I break math? Well, this guy is confused as well. Smiley face, glasses, nosed guy. Right there. He has no idea what's going on. What does 0 equals 0 mean? 0 equals 0 is a way of calling these two equations dependent. What that means is that regardless of what solution I substitute into this equation right here to make the left side equal the right side, that will also hold true for the original equation that I have right here. No matter what I plug into there to make this true, this will also be the same set. What does that mean? Well, as an answer set, it means infinite number of solutions. Let me kind of show you an actual example of what that actually means. Now, to do this, I'd have to actually come up with an xy value that works. Let me do 5 and 6. Oh, okay, yeah, I think 5 and 6. Okay, consider the solution set the solution 5 comma 6 right here. That's 5 for x, 6 for y. If I substitute 5 for x in this equation here, 7 times 5 is 35. And I subtract 5 times 6, I subtract 30. 35 minus 30 is 5. And that tends to pan out. So this is a solution to this bottom equation. All that means is that if this is a solution to the bottom equation, it's also a solution to the top equation. 5 times 14 is 70. 10 times 6 is 60. 70 minus 60 is 10. Now, is it just this one point that works? No. Any point that is on these, remember, these are actually lines. Any point that is on this line on the top equation will also satisfy the bottom equation. What that really means is that these two equations are the same exact line. It's one line on top of the other. So there's an infinite number of solutions. There's not just one solution. And that really does start to dispel why you would ever consider trying guess and check for this, right? I could have guessed and checked until I got 5 for x and 6 for y, or another answer could be 0 for x and -1 for y. But just because you get one of the answers doesn't mean you got them all. There's an infinite number of solutions here. And by infinite, I literally mean there's no limit to how many solutions there are. This is your answer here. Now, what clued me in onto the answers because the x's and y's canceled? Well, sort of. It's because this side is 0 and this side is 0. Now, if you got 0 equals 2 as an answer and all of your math was correct, this would actually be a no solution case. It would mean no matter what you plug in for x and y as a solution here, it would never actually work for this one here. Like if this said this, 12 as an answer there, this would actually be a no solution case. This would be exactly what it is we're talking about. 0 equals 2. Nothing that I plug in for here would ever work for me to plug in for there. These would be an instance of parallel lines. And good news for us, we get to graph next. And maybe we get to start to talk about that stuff again. Okay, solve each system by graphing. Now, in order to do this, a prerequisite of this, really, for this video, unless you're kind of learning it right now, but make sure that you understand your y equals mx plus b slope-intercept form equation. Because as I talk about the process of this problem and the answer, and what we get out of it, it's important to understand that the slope is your change in y values, your rise, divided by your change in x value, your run. The b value is a y-intercept, and it appears at the point 0, comma b. A y-intercept is a value of y when x equals 0. So substitute 0 for x, what you get for b. And that really just shows up in these equations here as long as they're written in that form. And they are. So number 7, the top equation right here, I'm going to go ahead and graph that in purple. Y equals 1/4 x plus 1. Okay, this 1 right here, when x is 0, your y value is 1. That means there's a point on this graph that's 0, comma 1. Nice. In order to find more points on this graph, one could use a table. But this slope thing has a nice little trick thing to it. This fraction should not be really a turnoff for anybody here. It really shouldn't turn you away from the problem, because this can say how much you want to rise from a point, and this is how much you can run with respect to that point. So if we rise from 0, 1, up 1, and run 4, this falls along the exact same rate as that 1/4. Every time we rise 1/4, we run 1 as well. You could kind of put these points in. I'm going to not really count those, because we're going to connect dots here in just a bit. Now, you only need 2 points to create a unique line, but for the sake of argument, let's go ahead and do another set, especially to talk about the fact that, you know, I rose 1, okay? I rose 1, that's a positive number, and I ran 4, that's a positive. Rise 1, run 4. Positive 1 divided by positive 4 is positive 1/4. Remember these slope triangles here? Now, I'm mentioning that very appropriately here because a positive slope goes up as long as you're going to the right. Okay, that's a positive slope. Now, I can find other points, which means it goes down as it goes to the left. So my point is, no pun intended, my point is in this, I can also go down 1 as long as I run 4 to the left. Running 4 to the left is a -4 there. Okay, -1 divided by -4 is in fact positive 1/4. Seems strange, but it's true. So here's another point that I could use here. And just to really make sure it makes sense, I could go from here, rise 1, run 4, and it looks like that's positive. So it looks like these make sense here, and every other graph I draw from here on out should be significantly quicker. Again, I want to reteach these problems, especially for those who really feel like they need this to learn what it is they're doing. So there's my graph drawing this line. Try and do as best as you can for that, for the sake of accuracy, because what's the whole idea of this problem? I have to find the point of intersection between these two. And I really want to make sure that I get this as accurately as possible to know that I did graph it correctly. Okay, I'm going to graph the bottom equation here in green, doing the same exact thing I did over here. My y-intercept value is at 0, -4. So I'm going to start 4 down from the origin right there. Now, my rise over run, I'm going to rise 3 and run 2, and I'm going to maintain that rate as long as I go. Rise 3 to -1, run 2 over here. Up 3, boom, 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 over 2. Hey, looks like we landed on a point we want. If I rose 3 and ran 2 again, I'm kind of off the graph, and same thing on this side here. So let's say that's enough points right there. All right, let's go ahead and graph this thing. Draw the line that goes through, and obviously that doesn't go through. Let me readjust it. Not bad. Did I really need this line? Well, at this point, right here, it looks like we realized what our answer probably is. This point of intersection, 4, 2, happens to be the one solution that satisfies both equations. This is much like if I solved this thing by substitution or elimination, I would get x equals 4 and y equals 2. Solving by graphing, we did the exact same thing. And this really worked well in graphing form because, look, we don't like fractions. This is already in slope-intercept form, and there's a graph there for us. Why not just try and graph it? Now, if your answer ended up landing on a fraction, such as, like right there, okay, maybe that's not as fun to do, and you can't guarantee that it's halfway in between. But as long as we give you a problem that's set up that it seems like, yeah, you'll get an integer answer, maybe this is the way to go. Especially when we say solve by graphing. And especially if you're given a final exam that's multiple choice, right? And you have another option but to look at all the graphs. And you're going to have to know how those things are graphed. Number 8, y equals 7/3 x plus 3. Same kind of idea. That 7/3, that's a bigger fraction, which means more counting for me. I'll kind of show you what I'm going to have to do with this one as my graphing area is so small. I'm going to start at 0, 3 right here. And ideally what you would do is you would rise 7 and you'd run 3. And the point would be probably somewhere way up here. Okay, way off my graph though. Very hard to scale that. So I'm not going to bother going up and to the right. Let's hope I have enough room to go down and to the left. Right? It's a positive 7/3. So as long as I fall 7, which is a -7, and run 3 to the left, that's a -3, I will find another point on my graph. What did I say? It takes 2 points to make a unique line? Yes, sir. And these are the only two that could really fit as I was doing this. So while more points are probably preferred, in this case, more would kind of be less preferred because I don't have them on my graph. They don't really fit. There's one of my lines there, the one in purple. Green, here we go. 7/3 x minus 1. Okay, well, same kind of ordeal like last time. In fact, this one, it looks like, this one might be a bit of an issue. Check this out. Start at 0, -1. Now, let's say I did want to fall 7 again, just like last time. Well, running off the graph. If I want to rise 7, I'm also running off the graph here. Check this out. 4, 5, 6, 7. I do have to get another point here. So for the sake of argument, let's say that I should probably plot this point up here. I'll get close enough. What? That's probably up right there. Okay, and over 3. 1, 2, 3. Okay, not bad. It's kind of as accurate as I'll be. We say these things are drawn to scale, and it sort of is. Okay, but the end goal really for us is to look at what this final solution set's going to be and interpret why that is. Okay, I made 2 graphs here, and your goal is, of course, to find the point of intersection of these two. And as you can see on this graph here, they don't actually seem to intersect. Now, the real question here becomes, if I extended these lines farther, because, of course, they go on forever, that's why we draw the arrows. If I extend these lines farther and I zoom out of my graph, is there a chance that I'm going to see these intersect later? In some graphs, absolutely, it's possible. Like, take a look at this one that I'm going to change right now. If I change it like that, look, they didn't intersect here, But if I extend farther, these actually would intersect somewhere way up there. I don't know where. But these two happen to be parallel lines. Parallel lines meaning they fly at the same rate. They're both rising 7 and running 3. We actually saw that initially, y equals mx plus b right here. These are parallel lines. Different y-intercept, same slope. That means it's not two lines on top. See, two lines could have the same slope and one could be right on top of the other, in which case that's not parallel because they intersect everywhere. That would be an infinite number of solutions case. This is one of those no solutions cases. This is one of those cases like I talked about if it said 0 equals 2, when I did substitution in the end, it might end up something like that. This one doesn't intersect. Not that it doesn't intersect where we're looking, it doesn't ever intersect. No solution. Now you might not have to graph that to know that, but I'm showing you the picture kind of as an indicative way of mentioning, like, okay, let's trust it. Let's trust it. I do at least. Solve each system by substitution. Number 9, y equals x minus 5, y equals negative 2x plus 1. Now, I was just mentioning that before, these problems were in y equals mx plus b, right? Number 7, number 8. These also are in y equals mx plus b, so it's completely okay to, graph these as long as they're drawn to scale and such. These ones don't have fractions, though, so maybe it's a little more convenient for us to find other mathematical means. So let's see what we got here. We got y equals this and y equals that. I'm literally going to call them this and that. If you have y equaling this and y equaling that, guess what? We're trying to find the same y value for both of these. So we want this y to equal that y. So what can we do? Substitution. If y equals this, this can take place of this y. And if y equals that, that can take place of that y. If y equals this and y equals that, then this equals that. Another thing this is called in your textbook is the equal values method. I tend to just call it substitution. In fact, it's probably the easiest type of substitution. Just don't really confuse yourself with the idea. If this equals y, this can take place of this y right here just fine. And you have that exact equation that we see down below. Okay, so we got the good part started off here where we're trying to find, solve the system, trying to find x and y again. So the end goal for all these equations here, including the elimination ones that we did before, is try and get one equation with just one variable. I can now solve for x now that it's all alone. But let's truly isolate x by moving it to one side of the equation. I'll go ahead and subtract them over. And in doing so, let's go ahead and add this 5 over to the right side, so I really do get the x's left by themselves. Negative 2x plus 2x is 0. Negative 5 plus 5 is 0. X plus 2x is 3x. 1 plus 5 is 6. 3 times the number is 6. That number is 2. When you divide by 3, that's the number you get. So, x is 2. What is y? I know you are, but what am I? X is 2. You can substitute it into either equation. It should work out. Just for the sake of argument, I'll do both of them. Y equals 2 minus 5. That's the top equation. Oop, parentheses. Which would be negative 3. Or y equals negative 2 times 2 plus 1, which is negative 4 plus 1, which is negative 3. No matter which value, no matter which equation I plug this value into, I should be getting the same exact result. And again, this is the only x, y value that works for both of them. So your final solution is 2, negative 3. Ordered pair. Ordered pairs. Remember, point of intersection. Number 10, same exact idea. Equal values method. If y equals this and y equals that, then this equals that. Again, finding the same y value for both equations. Okay, same exact stuff here. Let me do something I'm not going to call it the harder way, but if people tend to want to say x equals on the left side, then they tend to move x's over to the left side, which is okay. Just don't forget your signs here. Okay, I'll do subtracting 2x. Generally, whenever you see me do these problems, I tend to try and keep the x's positive, even if it means moving them over to the right side just early on. But right now, I'll move them to the left side and show you what sometimes arrives here. X minus 2x is negative x, or negative 1x. Negative 4 plus 2 is negative 2. Now, this is not your answer, right? Oh, in fact, we still need to find y, but this is not our x value. X doesn't equal negative 2. No, negative x is negative 2. The opposite of some number is negative 2. What is that number? Well, I think quite obviously we can say that number is 2, right? So what do you do to solve it? You can say that there's a -1 in front of here, so maybe you say divide both sides by -1. That's fine. -2 divided by -1 is +2. Maybe you can say you multiply both sides by -1. To be consistent, I'll do divide by, because it's kind of like -1 times x, right? So okay, so I'll go and say that x is 2, therefore. Let's go and solve for y. I'll do this without kind of any good old mental handiwork. I'll do it mentally. Y equals 2 minus 2. Looks like it's 0. So y equals 0, x is 2. Your final coordinate pair there is 2, comma, 0. All right, not bad, not bad. Solve each system by substitution. Okay, no problem. Let's go and keep working with this. Now, we're asking you substitution method, okay, not elimination method. Is elimination preferred for this set? Maybe, probably, because you kind of see the lining up. You say, if only I multiply these by 3 or divide these by 3. Yeah, but, you know, let's go ahead and satisfy their whims. Let's go ahead and do substitution. Now, for substitution, what's recommended is that you get one of these 4 variables isolated on its own side of the equation. In this particular instance, there's no real hassle of getting any of them by themselves, in the sense that there's no fraction values that will result in this stuff. However, I would argue that getting this y by itself is the easiest, because it's already kind of by itself by 1y, and it's only going to take us 1 step to solve. That doesn't mean it's the easiest way to solve this problem, but it does take the least amount of steps. How do I get y by itself? How do I make it say y equals? Well, I'm going to add x to both sides. Silly. Plus x plus x. So y is 4 plus x. I might write x plus 4 because I'm used to that mx plus b format. So y equals x plus 4. X plus 4 is one way to express y. So if I take this x plus 4 right here, I can substitute it into this y right here. Totally okay to do. And again, I'm using the other equation here because it's another way the problem is expressed, so to speak. In this particular instance, there's going to be something a little tricky here that you'll see. That you notice whenever I say something's tricky, you probably know what to expect as an answer. Now, when it comes to me distributing this -3, notice it's a -3 multiplied with this positive x and this positive 4, then both of these terms will become negative. So -3 times x is -3x. -3 times 4 is -12. So 3x minus 12 equals -12. Now, before I do any adding moving over, let's simplify these things. Combine like terms. 3x minus 3x equals 0. And let's add to 12. Do we have to add 12 to both sides? Take a look at your statement you have right now. All x's are gone. All y's are gone. You have -12 equals -12. Well, what did I mention before about that whole 0 equals 0 kind of business, right? If the left side equals the right side and all x and y terms are gone, then they're dependent on each other. This is one of those infinite number of solutions cases, just like last time. And that's what I was saying by, this problem's tricky or weird, different in a way. Same idea as before, infinite number of solutions. Now, if you don't believe me, really, and I'm not saying you should or shouldn't, but if you don't believe me, let's take a look at the original problem set we had here. Let's say, this y equals x plus 4. That was from the top equation, right? Let's say I took the bottom equation and got y by itself. Now, it's going to take a couple steps, and it's probably worth noting what these steps are because you might have to do this at some point. To get this y by itself, we might start by subtracting 3x from both sides. So it will say -3y equals -3x minus 12. Well, now how do you get y by itself? You divide. You divide everything by -3. Every term. This term, this term, this term. These are gone. These are gone-ish, right, also. And -12 divided by -3 is +4. So y equals positive 1x plus 4. Well, look, these two equations are the same. That means if we graphed them, that would be one line on top of another, so an infinite number of solutions. That's what we expected as an answer here. By the way, I didn't mention this before. Infinite number of solutions and all real numbers do not mean the same thing. All real numbers means I could plug anything into x and y into either equation and it should work for all of them. No. What I said was as long as something that you plug in here for x and y works for the top equation, it will work for the bottom equation. Okay, second problem right here, solve again by substitution. Let's do the same concept as I talked about before. Pick a variable that you would like to, get by itself, get isolated so you can play that substitution game. Okay, well, one that you actually probably wouldn't want to do is get this y by itself. And I didn't mention this x, I just said this y. I'll show you. Let's say I did get it by itself. Add 2x to both sides. 4y equals 2x plus 20. Divide by 4, what's going to happen? Well, 20 can divide by 4 just fine. 2 divides by 4, you're left with 1/2, or 0.5. We're trying to avoid using fractions if at all possible. I'm not saying fractions are the enemy, like as in they should be ostracized from math. I'm saying you should work with them or work around them, really. So, hey, how about getting this top x by itself? It'll just take us one step like last time, right? Get this x by itself. Let's add y to both sides here. Okay, not quite y equals mx plus b form, but x equals my plus b, maybe? X equals y minus 7. Okay, now I have y minus 7 as a way of expressing this in terms of x, and we are going to substitute in for x in the other equation right here. So let's see what we got. Negative 2 times x, y minus 7, plus 4 times y equals 20. Let's go ahead and solve for y first and use that to solve for x. Distribute negative 2 into the positive y and the negative 7. Negative 2 times y is negative 2y. Negative 2 times negative 7 is positive 14. Rewrite the rest. And just like last time, combine like terms. Negative 2y plus 4y is a positive 2y here. Now I can start to isolate the y terms by subtracting 14 from both sides. 14 minus 14 is 0, of course, which is why we did it. And we get 2y equals 6, so y equals 3. Let's use that solution to solve for x. Now, where should I solve for x? You might say, hey, one of these top two equations. That's fine. But you know what you purposely did here with substitution that I always really like about substitution? You literally wrote an equation where x equals, boom, right there. Let's substitute y in right here and solve for x. It's set up for you already. You don't have to do anything else. X equals 3 minus 7, which is negative 4. So your final solution set here is 3, negative 4. That is your point of intersection for those guys. All right, did a lot of substitution and elimination there. Awesome. Number 13, ooh, word problem. That's fun. Mike's school is selling tickets to a spring musical. On the first day of ticket sales, the school sold 1 senior citizen ticket and 6 child tickets for a total of $41. The school took in $47 on the second day by selling 1 senior citizen ticket and 7 child tickets. Find the price of a senior citizen ticket and the price of a child ticket. Now, it is entirely possible for you to find the solution to this by guess and check. I understand that. Formatting wise, though, the numbers could be way scarier. The question could be way harder. So you'd probably want to generalize your approach for a kind of word problem such as this one to figure out how to do it by a certain process that really works. Because it gets you to really understand what it is that you're doing. So first thing that you want to do here, and I'm going to go ahead and type out some steps here. The first step that we want to kind of do is find out what question is being asked. Find out what question is being asked. Okay. The reason why I'm saying that, and look, there's no question mark here, but find out what they want you to tell them. The reason why is because the question that they're asking is the thing that they don't know and you don't know. It's information they didn't give you. It's information you have to find out. Things that you don't know are called unknowns. Unknowns, another word for those, are variables. So that leads me to step 2. Define your variables and be specific. I'll explain why here in just one second. Be specific. Okay, so what this means is you're going to create two variables here. And by two, I mean because the two things we don't know are the price of the senior citizen ticket and the price of the child ticket. These variables will be used in your equations, right? And in order to be able to make these equations, you really have to know what sentence it is you're creating to make this statement. Now, this word problem here, number 13, and I believe number 14 have the same format of question. Maybe 14 is just a little more difficult to solve. So unfortunately, we will not be very varied with this variable definition stuff. But I'll show you what I mean by be specific when I actually create them. Okay. The third thing, as I just kind of alluded to, was create equations based on the information, based on info from problem. Okay, so based on the information there, you're going to create equations, and what it helps to do is to say the stuff out loud. Say it out loud. And the reason I say that is because if you have specific variables defined that way, then when you say the thing out loud, your variable is transcoded from the sentence that you said. And again, it sounds kind of strange. Again, when I do the problem, I think you'll understand it. Finally, solve the equation, in any means necessary. Answer in a sentence or words using units. The question they ask you, the whole word problem is in words, right? So what we want to do is be able to reply back in words. If someone asks you, how is your day? I guess you could just answer, say, good, right? But if someone says, how is your day? Your better answer really is, my day is good. So you're repeating back what they said, and if that just makes sense. Okay, find out what question is being asked. Your unknowns are your variables, and let's define our variables. I think these are kind of all one step. So it's being asked to find the price of the senior citizen ticket and price of a child ticket. So I do not know how much a senior citizen ticket costs. I do not know how much a child ticket costs. Those will be my variables. I can use the letters X and Y, S and C. I think for this one, I'll just do X and Y because S can look like a 5, especially my S's. So here's what I'm not going to do. I'm not going to let X equal senior citizen ticket. Close. It's just not specific enough. Why do we have to be specific? Well, let's say we get an answer in the end. Let's say we get X equals 5, which who knows, that might be the answer. 5 what? 5 senior citizen tickets? Is that our answer? Was the unit this right here? No. Was it the weight of the senior citizen tickets? Was it how old each senior citizen is? Be specific about what this number is representing. I know that you're distinguishing it from child ticket, but senior citizen ticket, it's not how many there are, it's how much they are. It's how much they cost. Okay, so what I'm going to do is I'm going to specifically state, it's kind of in the question itself, the price of the senior citizen ticket. And the unit even is dollars. You could say number of dollars of senior citizen ticket. Okay, I'll let X equal price of senior citizen ticket. I'll let Y equal price of child ticket. And that too will be in dollars. That's being specific. Okay. And that might not seem like a big deal to you. It depends on how good you are at setting up equations. Look, if you know how to set up the equations, then maybe it isn't as big of a deal. Depends on what's being asked of you from your test maker, from your test grader. Create equations based on info from problems. Say it out loud. I guess not during a final, but say it out loud in your head. Okay, I have a sentence right here that gives me information about first day ticket sales. Selling 1 senior citizen ticket and 6 child tickets for a total of $41. If I sell 1 senior citizen ticket for however much they cost, I will have made 1 times the number of tickets sold. Excuse me. One ticket sold times the cost of the senior citizen ticket. If I add that to the number of child tickets I sold plus the price, times the price of each child ticket. This number also is the total number of dollars made from selling 6 child tickets. I will have collected $41. Now, when I did this whole equation stuff, the big thing is there needs to be what's called unit agreement. This is dollars plus dollars equals dollars. What you can't have the units be number of seniors plus number of children equals number of dollars. You can't say X plus Y equals 41. That's not what this stuff says. And it's not even the price. This is price of one of them. So you have to say, okay, well, there were 6 child tickets sold, so how much, whatever. Now, just so you know, this doesn't seem like a lot of people will be showing up to this musical. Well, I guess it's the first and second day, but even then, come on, you're supposed to be selling out, right? Anyway, so there's 1x plus 6y equals 41. Second equation is based on this information right here. The school took in $47 in the second day by selling 1 senior citizen ticket and 7 child tickets. So 1 senior citizen ticket times the times the price, so you have to see that, times the price of each senior citizen ticket is how much made for all senior citizen tickets. Plus the number of child tickets sold times the price of each child ticket will give me the number of dollars made from child tickets. So when I take all my money from selling these, with all my money from selling these, I've got $1,047. Boom, those are the 2 equations we have there. And these 1x's don't even need to say that. They could just say x at this point. Up to you either way. So we get x, well, it needs to still say an x though. So x plus 6y equals 41, x plus 7y equals 47. Time for you to solve. A lot of different ways you can go about it, because I'll probably do elimination next time. Let's just have fun and do substitution this time. I'm actually going to rewrite both of these equations so that x is actually by itself. Subtract 6y, x equals negative 6y plus 41. Subtract 7y, x equals negative 7y plus 41. If x equals this and x equals that, then this equals that. I can set these 2 things equal to each other. This x equals 5 is probably, it's not necessarily the answer. Negative 6y plus 41 equals, this is a 47, equals negative 7y, there would be no solution. Negative 7y plus 47. It would be on the second day they ripped them off, or on the first day. Add 7y over, you'll get positive 1y here. Subtract 41 over, you'll get 6. Y equals 6. The cost of each child ticket, the price, is $6. What's the price of each senior citizen ticket? Well, let's substitute 6 for y into one of the 2 original equations. Or actually, into any set. Let's do this one. X equals negative 6 times 6 plus 41. X equals negative, hey, what do you know? What did we get? X equals 5. All right. Well, so we did get that answer. Regardless, that's 5. That's not 5 senior citizen tickets. That's the price of each senior citizen ticket. They're each $5. So if I'm going to write the final thing, and look, this is not an ordered pair either. Especially, you're probably going to be defining a lot of variables that aren't x and y. So don't get used to writing ordered pairs for these. Leave something in terms of words. The price of each child ticket is, I think it's $6. And the price of each senior citizen ticket, hang on, let's shrink this. Each senior citizen ticket is $5. And that answers the question that was being asked. We set it up, we solved it, we're good to go. We'll do another problem, I think just like this one. The school that Jimmy goes to is selling tickets to the annual talent show. On the first day of ticket sales, the school sold 8 senior citizen tickets and 3 student tickets for a total of $92. The school took in $52 on the second day by selling 4 senior citizen tickets and 3 student tickets. What is the price of 1 senior citizen, 1 student ticket? Okay, so it's back to the same stuff as before, assuming we use the same variables x and y to represent senior citizen and child tickets. Oh, this is student tickets now, but that's okay. Let's, for the sake of time, let's jump straight into it. As you saw last time, we'll do 8 senior citizen tickets times the price of each gives you how much money you're going to make for all 8 of those. Three student tickets times the price of each gives you how much money you're going to make on all of those. Collectively, $92 on the first day from this accumulation. Day number 2, 4 senior citizen tickets times their price plus 3 student tickets times their price equals 52. What is the price of 1 and 1? So let's solve for x and y. Okay, I said I did the other one through substitution. I'll do this one through elimination. That's fine. These numbers are the same, so close. Let's get additive inverses. Let's take one set and multiply them by -1. And as I really don't like more negative numbers, let's make the smaller numbers negative. So -4x minus 3y equals -52. Bye-bye. 8x minus 4x is 4x. 3y minus 3y is 0y. That's just 0. Normally that cancels. 92 minus 52 is 42. Just kidding, it's 40. Divide by 4, you get x equals 10. Boom, solved for one of them. Now, as we don't have a y equals equation yet, we're going to have to substitute it into one of the original equations. I'll use the smaller numbers here. 4 times 10, which by the way is 40, that's how many dollars made from selling senior tickets on that day, senior citizen tickets. Plus 3y equals 52. 40, we said that was 40. Okay, 3y equals 12 and y equals 4. So to answer this question again, like the last one, remember x is representing number of senior citizen tickets, y in this case is representing number of student tickets. Excuse me, not number of. See, that's why I have to write them. The cost of each. The cost of each. The price. See, I really have to define these variables for myself. The price of one senior citizen ticket is $10, and the price of one student ticket is $4. Hey, we answered the question. I think these are the only word problems in this whole packet. So they're in and out of the way early, but we've done a lot of system solving. A lot of system solving. Now we're, oh, this shouldn't say factor each completely. This should say sketch the graphs. Sorry about that. Sketch each graph. My mistake. Now we're getting into exponential functions. And these are in a very specific form here that looks like y equals a times b to the x power. Now I'm going to try and avoid using tables when it comes to the full idea and understanding of this. In fact, I hope over time you really get the understanding of what's actually happening. But if we did start with the table a little bit here, I would plug in some values for x and get some values out for y. Without a calculator, okay, I'm going to do this whole thing without a calculator. Without a calculator, understanding what these answers will be, even as fractions or decimals, is key. I'm going to be using fractions when I have to, which means I'm going to also be dealing with some negative x values here. So I'm going to create some values and talk to you about each one of them and see if you can make sense of its pattern, because this does kind of fly in the face of geometric sequences, which we'll do near the very, very end of this video. Let's say I substitute 0 for x. Now this is, no, actually start with this one. Let's say I substitute 1 for x. This is 2 times 3 to the first power. 3 to the first power is 3. 2 times 3 is 6. X is 1, y is 6. Substitute 2 for x. 2 times 3 squared. You do 3 squared first. 3 squared is 9. 2 times 9 is 18. And then substitute 3 for x. 3 cubed is 27 times 2 is 54. As you can tell, I won't be able to graph this point, but I still want to talk about what's happening here. Every time x increases by 1, as you can see by this pattern here, it does appear that we are multiplying by 3 one more time than we did the previous time. Times 3, times 3, times 3. And if we're to follow this example, that means that going this way, we'd be dividing by 3. Now, I'll make 2 points on these two things that I'm saying here. First of all, is this correct? Yes. If there was a plus 1 out here, that would change everything, but there isn't one out there, so let's leave it there. One thing I want to say on the times 3 thing, that's what exponentiation is. Every time this number increases by 1, 3 squared means 3 times 3 twice. 3 to the 100th power means 3 times 3 100 times. That number literally means how many times you're multiplying by 3. So yeah, every time I increase x by 1, I'm multiplying by 3 one more time. That makes sense. What's the difference between 3 to the 4th and 3 to the 5th? 3 to the 5th is 3 times larger than 3 to the 4th. These two are the same thing. So every time I increase x by 1, yes, I am multiplying by 3. That is true. So if you wanted to figure out what 4 is, besides plugging it into here, you could take 54 and multiply it by 3. Right? You could just do that, because that's kind of what I'm going to do for this side. I'll tell you about another way of going about it, though, because both might really help you. 0 power. If you didn't know what 3 to the 0 power was, let's say you thought it was 0. Let's see if I can prove you wrong by saying this. By going to the left, I'm dividing by 3. As you can see, 18 divided by 3 is 6. What is 6 divided by 3? Well, that number is 2. And that is the correct answer here. So, what is 3 to the 0 power? 2 times what number would give us 2? Well, 3 to the 0 power is 1. You don't multiply by 3 at all. You don't even start with 3. It's just 1. So, anything to the 0 power is 1, which does mean, as we kind of see that 3 in our equation as like a growth factor, this number kind of represents starting value. As long as the exponent becomes 0 here, this goes away, this becomes that number there. It's kind of like your y-intercept, which it is. So there's the 2. Okay, what's 2 divided by 3? That's 2/3. What number goes here? What's a negative 1? How does that work? We'll take a look at that after I do this recursive process here. Negative 2, negative 3. What's 2/3 divided by 3? That one's tough for people. Most people want to go to the calculator. Most people might even mess it up in the calculator because some order of operations issues. 2/3 divided by 3. That number is the same thing as what 2/3, 2/3 divided by 3. Think of that as 2/3 divided by 3 over 1, right? Divided by 3. That's the same thing as 2/3 times 1/3. So instead of me stating divided by 3 here, I think it might be more helpful that I say times 1/3 for a couple reasons. One, I think it's easier to do this. 2/3 times 1/3 is 2/9. So that is this number here. And 2, look, you're going to be dealing with common ratios that are, growth factors that are fractions. You'll never see this thing as like a division. I mean, a fraction is a division, but you'll never see it outside of that format. You will be multiplying by 1/2, which we can transcode as dividing by 2. We'll get to that one in a bit. 2/9 times 1/3 is 2/27. Okay, so small numbers. Now, how do we use negative exponents and relate that to this stuff here? How come 2 times 3 to the negative first power is 2/3? Well, if you remember how negative exponents work, it's the same thing as 1 divided by 3 to the positive first power. So that's 2 times 1/3. 2 over 1 times 1/3. That equals 2/3 there. 3 to the negative second power is 1 over 3 squared. So that's 2 times 1 over 9. So that's 2/9, etc. So this stuff all has common rhyme and reason. I'm going to be using these points to graph with, and some of them don't really fit, especially the one, 2/27. That's a hard thing to graph. It really is. So I'll just do the best I can here and work with this. I have 0, 2, 0, 2, I believe 1, 6, right? You multiply by 3, and 2, 18. So I can fit those points on here just okay. Okay, the other numbers, 2/3, 2/9, 2/27. This is where, the fraction probably is better than the decimal, because you're saying what fraction of 1 is that number. Well, 2/3 of 1 is, that is 2/3. So go 2/3 up from 1. Go 2/9 up from 1. And how do you do that? Well, it's a little less than 1/3. Just do your best. And 2/27, might as well be on 0. But it's not exactly, right? Because the whole idea of exponential functions, one of the big keys, I'm going to zoom out here. One of the big keys about exponential functions is that, getting too far zoomed out. You will never, ever be able to get 0 for y based on substituting any value for x. There's no value of x that you can plug in that you'll get 0 for y. No matter how far negative you get, you can do 2 to the negative 100th power. That still is 1 over 2 to the 100th power. 3. That is 1 over 3 to the 100th power. Okay? There's this thing called an asymptote right here that says you shall not cross. It never, ever, ever will, no matter what value of x. If you would like to know, although it's not going to be asked about, your domain is all real numbers. You can substitute any value for x you'd like. You will always get a value out for y. Your range, what values of y will we get out? It looks like we can plug in massive numbers for x and we'll get massive numbers for y. Yeah, that seems to be true. But here in this case, we're going to be y is greater than 0. Any values we get will be 0 or greater than. Okay? We will not get anything 0 or less, anything greater than 0. Only positive numbers as a result. Okay, that's enough with that problem there. I'm going to do this one a lot more quickly as a result. Even more so, I might not even have to use a table. What did we talk about with this first number here, the a value? The a value represents your y-intercept. Because y-intercept is the value of y when x equals 0. 1/2 to the 0 power is 1. 3 times 1 is 3. So when x is 0, y is 3. That is one of our points. Then every time x increases by 1, we're going to multiply by 1/2 one more time. So when I increase x by 1 here, I'm going to multiply 3 by 1/2. Well, what is 3 times 1/2? That's 3 halves. 3 halves, the fraction. That's also 1 and 1/2. If you do use the calculator, it'll say 1.5. Multiply 1.5 times 1/2. Here, let's think of it as money instead. Half of $3 is $1.50. Half of $1.50 is 75 cents. Half of 75 cents, now you're like, oh, I can't do that. Let's see, it would be 37.5. So, it gets lower. Basically, the number is half of what it was before. So I could probably just use these heights and kind of guess. Oh, half, yeah. But you keep taking half of a number. It's like folding a paper in half. You keep folding a paper forever and ever, which you can, by the way, I think is like only do 7 times. You can try it. If you were able to fold a paper in half forever and ever, would it ever disappear? No, it wouldn't ever become 0. Could the paper become negative? No, definitely not. Okay, so multiplying something by half is the same thing as dividing by 2. So what do you think dividing by 1/2 is the same thing as? Well, this will be the same thing as multiplying by 2. So we divide by 1/2 this way, we're multiplying by 2. 3 times 2 is 6. 6 times 2 is 12. 12 times 2 is 24, which is out of reach. So I'm just going to go ahead and draw the graph right here. As best as I can. I'll do kind of the shady way here. It's a curve, right? Keeps curving down, and it will start to flatten out a little bit. Never crosses 0. I like to do these little half arrows to say it's going forever, but there's a point that it's not crossing. Right? It's not crossing this y equals 0. When you take Algebra 2, you'll be learning about shifted asymptotes. Same with pre-calculus. Asymptotes that are not at y equals 0. You'll be playing with a bunch of different kinds, and hopefully you'll get better and better at it. You can always use a table for these problems, but please recognize the instance of this problem here. If your b value, your growth rate, is greater than 1, then your numbers are going to take off. They're going to jump. So if b is greater than 1, it's going to go upward because you're multiplying by a number larger than 1. If b is less than 1, like between 0 and 1, you're taking a fraction of something. So you're making it smaller and smaller as you go. Y-intercept, right? Y-intercept. So those are good keys. Domain here is also all real numbers. Range is also y is greater than 0. Nicely done. Let's zoom back in. Okay, factor completely. That's where I meant to put this. Factor each thing completely. N squared plus 12n plus 20, and 3v squared minus 3v minus 36. Okay, I'm not going to beat around the bush here too much. There is truth to the fact of the matter that while you can use a diamond and a rectangle, that generic rectangle, to do the factoring process, that tricky stuff, if you've caught on to the fact that as long as your quadratic coefficient is the number 1, then 2 awesome things happen. First of all, your answer in factored form, if it's factorable, would appear as n here and an n here. The second thing is these two numbers right here are also the numbers you end up writing to the left and right of the diamond. What's the question that we ask ourselves when we're trying to compute that diamond? The question is, what two numbers multiply to blah, blah, blah and add to blah, blah, blah? Well, the multiplying number is always what this number times this number is. You see that in your generic rectangle. You've talked about going across this way times this way, right? But as long as this number is 1, 1 times anything is just that something. So guess what number this has to multiply to? 20. We need two numbers that multiply to 20. Those two numbers will add to this linear term here, 12, that coefficient, or 20n squared and 12n. I'll just use the numbers 20 and 12. Now, what two numbers do that? You might already know. In case you don't, you can either mentally or physically pair up all factors of 20 and try and do as many as you can list. Boom. Consider the fact that the product is positive, which means either both numbers are positive or both are negative. And the fact that the sum is positive must mean then, therefore, that both are positive. Which one gives you 12? Looks like 2 and 10. So the answer to the question, what two numbers multiply to 20 and add to 12 is 2 and 10, also answers your factor question. What is this in factored form? It is n plus 2 times n plus 10. If you want to know if you're right, what can you do? You have two options. Number one, the safer option, distribute this back and determine whether it matches up with this. Number two, the idea, and I'll talk about it with number 18, the idea of factoring is that you are re-expressing this quantity right here, which means that this and this are the same thing for all values of n. So if I actually substituted in a number for n, like 3, I should get the same value here that I would here. 3 squared is 9, 12 times 3 is 36, 9 plus 36 is 45, plus 20 is 65. Okay? 3 plus 2 is 5, 3 plus 10 is 13, 5 times 13 is also 65. So while you'll run into some false positives, like if you plug in 0, a lot of times you'll get a false positive. If you plug in 1, there's a chance of it. Try number 2, 3, -3, something like that. Or 10, just something larger. But anyway, there's your answer. Okay, this one you can't do the exact same thing with. You would have to use, as long as there's a number out in front of your quadratic term, the quadratic coefficient that's not 1, you will have to use diamond and rectangle. Unless there is a common factor existing in all three terms. If all three terms are divisible by the same value, besides 1, then you can factor that value out. All three numbers here can divide by 3. 3 times what number, or 3 times what gives us 3v squared? That would be 1v squared. See that v squared? It has a 1 in front of it. 3 times what gives us -3v? That's -1v, or minus v. 3 times what number gives us -36? -12. If there's a common factor, oh boy, this helps you so much more than anything else. There's so many reasons why this is helpful. I will talk through them, but because I'm not going to be doing the other way, I will not go through that other way. Okay? I'll explain to you why after I solve this one. Now that the 3 is factored out, the one thing you do have to remember is that your final answer needs to still have a 3 there. Okay? Now, I already know this thing will have parentheses here, assuming it's factorable, and that I know because this is a 1v squared, it will be v this times v that. Now the question I need to ask myself is what two numbers multiply to -12 and adds to -1? Let's check our factors of -12 and see what we can come up with. Excuse me, let's just try 12. 1 times 12, 2 times 6, 3 times 4. Now a negative product means that one of your numbers will be positive and the other number will be negative. Because your sum is negative, that means the negative number will be larger. So as I wrote the smaller numbers here and the larger numbers here, let's try 1 minus 12, 2 minus 6, and 3 minus 4. It looks like positive 3 and -4 give us that result. So these will be the two parts in my answer. V plus 3 times V minus 4. And that is your final answer in factored form. Now, as I factor that 3 out, I did mention, don't forget it. Don't write it like this. This is not the same thing as this was. This is 3 times smaller, in fact. So So make sure that that 3 is a part of it. You do want to be able to substitute a value in for v and make it match here no matter what. Okay, so there's that part. Second thing I said, why did I look for a common factor first? Well, let's say I didn't look for a common factor first. That would mean that unless you know how to mentally factor these kinds of things, you would automatically be going to diamond and rectangle, which does mean a lot more work there. And guess what number goes on the top in your diamond? It's not a negative 36. It's negative 36 times 3. That would have been negative 108. Do you know how many factors of negative 108 there are? There's 1 times 108, 2 times 54, 3 times 36, 4 times 27, 6 times, hang on, I'm doing these in my head, 18, 7 doesn't work, 8 times, anyway, there are a lot, right? 9 times 12, there are probably 6 different pairs of factors, and you'd have to, you know, I mean, I'm doing that without a calculator. You'd probably use a calculator and test it out. It takes a long time. And, by the way, then you'll come up with an answer that probably looks like this, or like this. And then you'll say, okay, I'm done. But guess what? We have to factor them completely, which means just this common factor is not enough. Just this stuff's not enough here. These things still have common factors. 3 and 9 are divisible by 3. 3 and negative 12 are divisible by 3. You would have had to make it this final answer right here still. So there's still more to go for those kinds of problems, and you know, it just takes some time to do. It's always recommended that you get here so you can skip diamond rectangle. You have much smaller numbers to work with, and as long as you can retain that 3 in your final answer, there's nothing to be forgotten after you factor out the quadratic, assuming that it is factorable. So there's a lot to be said there. You know, like I said, I'll be speeding that up more and more as I go. I want you to really understand what it is you can do to help expedite your processes there. Okay, let's keep factoring. So like I said, I'm going to go quickly now. 1x squared. All I need to do is answer the question, what 2 numbers multiply to positive 16 and add to negative 10? Let's try this without writing them down this time. First of all, your answer is going to appear like this. Full bore straight up. X, X, 2 other numbers here. Factors of 16. 1 times 16, 2 times 8, 4 times 4. Our product is positive, which either means both numbers are positive or both are negative. Because the sum is negative, that means both are negative. So let's try those factors again. Negative 1 minus 16 is negative 17. Negative 2 minus 8 is negative 10. Oh, ding, ding. Our numbers are negative 2, negative 8. We are done. Again, all the double checking in the world you'd like to do. If you don't understand the mental stuff, go to the diamond and rectangle. Completely fine. Just make sure you're understanding the efficiency behind what really helps here. And this will help you with your times tables and your negatives and such. I'll try and do it again here. 1x squared, right? X and x. 2 numbers that multiply to negative 48 and add to negative 2. Well, 1 and 48, 2 and 24, 3 and 16, 4 and 12, 6 and 8. And that's it. Negative product means one number negative, one number positive. Negative sum means larger numbers negative. 1 minus 48, nope. 2 minus 24, nope. 3 minus, what was it, 16? Nope. 4 minus 12, nope. 6 minus 8, yeah, 6 minus 8 is negative 2. So positive 6, negative 8. So see the testing there, you know, it's, I guess you call it trial and error. But the testing involved is, well, it's necessary, first of all. It is. But we've filtered out to we've filtered it out to so few possibilities, right? There's just not that much you got to really look for. And that's key. That's really what's going to help you out with these problems here. Okay, factor each completely. Let's keep going. What 2 numbers multiply to negative 8 and add to positive 2? Well, there's 1 and 8 and 2 and 4. Negative product means one number positive, one negative. Positive sum means larger numbers positive. Let's try 8 minus 1. No, that's 7. 4 minus 2. Ooh, that's 2. Hey, it works. Plus 4 minus 2. If there's one way to speed up time in this stuff, it's that when you have repeat problems of the same caliber, you just mosey through them and make sure people hear the answer. Oh, b squared, but it's a 1b squared. That's okay. What two numbers multiply to positive 25 and add to negative 10? There's 25 and 1. There's 5 and 5. Positive product, negative sum, both numbers negative. Negative 25 minus 1 is negative 26. Negative 5 minus 5 is negative 10. If you have this factored form, this also might be another answer that you see. And in fact, if it's multiple choice, you'd have to kind of know that this is the same thing as that. Anything times itself is that number squared. Anything times itself is that number squared. So this factors down, better yet, to that right there. We've done this with completing the square, right? Whew, we keep factoring. Hey, no problem. The only thing now is that this number is no longer 1. Not only that, these are not there's no common factor here that's not just the number 1. If this was a 3, yeah, we could divide these all by 3, but that still wouldn't diminish the fact that this is still not going to be a 1. So, okay, we got to work with this one a little more strenuously. Hey, give me my diamond. Hey, give me my rectangle. Now, I do hope that as you continue to take more and more math, you say that although you trust the diamond and rectangle process, there is a faster way of going about it. It's called mental math, and it does require knowing what you're doing, knowing what the diamond does, and understanding all that. The more you do it, the more accustomed you'll feel to it. Just know you always have a fallback plan of being able to use the diamond and rectangle. Now, the rectangle has an actual purpose. These are sub-areas of the area of the entire rectangle, a base times a height, if you will. This sum is also represented in that rectangle. 9n squared and 1 have to go across from each other for the simple fact that there are no factors of n over here, but there are factors of n here and here. These two numbers will somehow combine and become 6n. We have to figure out what two numbers add to 6n by figuring out also what two numbers multiply to become the same thing as 9 times 1. 9 times 1 is 9, so what two numbers multiply to 9 and add to 6? Look, I won't beat around the bush. That's 3 and 3. So these two numbers go here. 3 and 3, they have n's attached to them. You might have seen 9n squared and 6n. You know, I kind of tend to avoid writing those because I know I'm going to write an n here later. Completely your call. I'm going to leave those out for the most part, though. So I know that n squared is a matter of n times n here, especially because this also has an n involved. So this can either be like 9 times 1 or 1 times 9 or 3 times 3. There's only one of them that's going to work because there's no common factor involved. In this case, 3 times 3 is the only one that's going to work. How come? Let's try 9 times 1. If this were true, then this is 1n, this is 1n. That's how that's how rectangles work. Opposite sides are equal. And 1 times what number gives us 3? I guess that number's 3. That works out. This one, though, doesn't really work. 9 times what number here gives you 3? Well, it's 1/3. And when we factor, we're talking about integer factorization. What works with 3 and 3, though, is that as 3 times 3 is 9, I can multiply 3 by an integer to give me 3 here, and 3 by an integer to give me 3 here. Now, 3n times 3n is 9n squared. This is 3n. This is 3n. And double check this one. 1 times 1. That's 1. That works out. This ends up being your factored form. If this is your original sum, the product, base times height, is 3n plus 1 times 3n plus 1. And much like the last problem that we just did, if it's the same thing multiplied by itself, you might see it written as 3n plus 1 quantity squared, just like that. So that seems to work out pretty well in our favor as well. And yeah. And again, if you've done the mental math, then you kind of know that these things that happen here, this is called a special case. Right? This one here is also called a special case, and there's something at the end I'm going to add to this that I actually haven't talked to my class much about, but I will. Okay, we're going to factor this quadratic here. Now, first of all, there is no common factor, not even of b, much less of these values. 25 and 4 can't divide by the same thing. However, unlike all the other quadratics, this one only has two terms. It has your quadratic term, and it has your constant term. We are missing the linear term inside here. If we were to rewrite this as a trinomial involving a linear term, we can do that. We would just have to make sure that its coefficient is the number 0. If this helps you recognize how it is that you work a problem like this with diamond and rectangle, by all means, use that. Because when you try and say what two numbers multiply to this and add to this, the thing they add to is 0. So when you're doing the diamond, note that this number, 0 or 0n, goes right there, which is a nice key thing to factoring a problem like this. Now when I go to my rectangle here, this is where things get a little different. We got 25b squared. 25b squared. I think I said 0n. I should have said 0b. 25b squared here, negative 4 here. 25 times negative 4 is negative 100. So when you try and figure out what these two numbers are as they multiply to negative 100 and add to 0, let's think back at elimination method. The only two kinds of numbers that can add to 0, besides 0 and 0, are two additive inverses, numbers that are exact opposites of each other, like 6 and negative 6. But 6 times negative 6 isn't negative 100. So what two numbers do you multiply to get 100 that are the same? Square root of 100, that's 10. 10 and negative 10. 10 minus 10 is 0. 10 times negative 10 is negative 100. So that's 10b and negative 10b. And now we play the factoring game. b and b definitely go here. 25 could be 25 and 1, but 25 times this isn't 10. This is going to be a 5b and a 5b. This problem is going to look a lot kind of like this problem with one big exception. 5b times positive 2 is positive 10b, but 5b times negative 2 is negative 10b. So when you factor this thing down, it is 5b plus 2 times 5b minus 2. This is your final answer. This isn't anything squared. This kind of problem, though, and I'm not going to dive into it too much, just if you've heard it before, if you hear it later, this kind of problem is called a difference of two squares. All they mean, two squares. All they mean is that if you have some a plus b times a minus b, this does equal a squared minus b squared. A binomial, quadratic, such as this one here, two terms with a quadratic here, and that if a is if a is 5b, like a plus b, and b is 2, and all that stuff, well, then this is 5b squared minus 2 squared, which is 25b squared minus 4. So there's a relationship here that the more you do this, the better off you are with that special case of factoring. For the time being, with my class, I'm good with you just factoring down and out. If you check on the pattern yourself and you pick it up, that's only good for you. But make sure you do it correctly. Okay, solve each equation by factoring. Okay. To begin with, this problem is already factored. There is nothing else to factor. The worst thing that you can do for this problem right now is distribute. Okay. And the reason I laughed is because many of my students were inclined to do that, right? They distributed, and then they got this trinomial, and then what did they do there? They factored, and then they got back down to this, and they solved the way you're supposed to solve. Well, it's already factored. Whatever this could have been written out, however, it would have been plus x plus 10, so plus 11x plus 2. They could have written it out like this to begin with, and you would have factored it down to this, and then you would have solved. So don't help them out by going backwards. Let's go forwards. What we're going to use is called the zero product property. Zero product property. If one number, and x plus 2 is a number just like x is, if a number times another number equals 0, the two things that are true is one of these numbers has to be 0. One of these has to be 0. It is impossible to multiply two non-zero numbers together and get 0 out. Mathematically, physically, theoretically, it's all impossible. The second thing about this that's so special is that as long as one of these numbers is 0, then the whole result is 0. And I know that that seems a little obvious to you, but you don't want to make the mistake of doing that in a case when it's not set equal to 0, like if it was set equal to 10. There's no such thing as 10 product property. Plus, if one number times another equals 10, that doesn't necessarily mean one of the numbers has to be 10, right? We've heard of 5 times 2, right? It doesn't have to be 10 times 1. It could be negative 10 times negative 1. Plus, as long as one of the numbers is 10, then the other doesn't have to be 10. What? You know? That's kind of weird. This only works for 0. There's no other whatever product property. So that's why if you want to set it equal to something else on the other side, you'd have to solve by completing the square. For factoring, and even for quadratic formula, set it equal to 0. Work the rest of the way. These are your two answers here. X equals negative 2, x equals negative 1/5. Okay, this problem here, it's already factored down, of course, as well. So I will use zero product property, only it looks like I should use the letter n. I will use zero product property one more time. You know, through pattern recognition, you might ask, hey, Mr. Robinson. Oh, speaking of patterns. Hey, Mr. Robinson, is it true that your answer is opposite the factor? What I mean by that is, this is a positive 4. This answer is negative 4. This is a negative 3. This answer is positive 3. Is your answer always the opposite? Well, if your linear factor here is a 1n and a 1n, yes, of course, because it's the number that we want to plug in here to get 0. 3 minus 3 is 0. Negative 4 plus 4 is 0. Same with negative 2 plus 2. Doesn't look like this answer is negative 1, though, right? This answer is negative 1/5. So I wouldn't always play guessing games with everything. It is true if it's a 1n or a 1x, yes, it's the opposite number. You can probably skip the step. This step is probably more geared towards something like this, where you really have to work hard at finding out that x value. By the way, negative 0.2 is a perfectly acceptable answer because it is not rounded, but you'd either have to know it or use your calculator to get it. Either way, I recommend the fraction a lot more. Numbers 27 and 28 solve each equation by factoring. Okay, we're getting back down to what I was saying before about zero product property. If you'd like to solve by factoring, by all means, please do so. Just make sure that your equation is set equal to 0. Okay? I'll let you know right now, look, I could factor n squared into n times n. That's fun. And I can factor out a negative 16 from here and all of n plus 4. That also is fun. But this doesn't really get me anywhere. I'm not really working my way toward an answer. What I have to do is rewrite this quadratic in standard form, where I have my quadratic term, my linear term next, plus 16n plus 16n, and my constant term next, plus 64 plus 64. This is all equal to 0, because these canceled out here. So now I have this thing in standard form. I have it set equal to 0. Now it's time for me to factor, and then I will solve it. As this is a 1n squared, just like factoring before, this will be some sort of n times n thing here. This is all equal to 0, by the way. All I'm doing is rewriting this part in factored form. The two numbers that multiply to 64 and add to 16, save some time, let's call it 8 and 8. That's true. Okay, you have two ways of going about this. Now that you've done completing the square, I will tell you that second way as well. First way here, you can say either n plus 8 equals 0, so n equals negative 8, or n plus 8 equals 0, so n equals negative 8. Gee, I wrote my answer twice. That's kind of weird. I guess you can do that. There's nothing wrong with it, but the fact of the matter is the only answer here is negative 8. So you can do that. Okay. What's entirely okay as well here is you can merge these into n plus 8 quantity squared. Why might you want to do that? Well, maybe you practice completing the square. But taking the square root of both sides, right, gets you to that. This cancels out the square thing. So n plus 8 equals plus or minus 0. There's no such thing as plus or minus 0. Make sure you don't write something like that. But you know what? It's better that you do than not. It's better to get in that habit of plus or minus. Anyway, subtract 8, n equals negative 8. Plus 0 or negative 8 minus 0. So n equals negative 8 is your answer, whether you use zero product property or the perfect square, this and that, because this was a perfect square trinomial, actually. So there you have it. Nice. Okay, number 28. A squared minus 3 equals negative 2a. Same kind of thing. You want to get this thing set equal to 0. Okay, so let's add the 2a over here, and I'd highly recommend you get that written in the middle. really getting that idea of quadratic term, linear term, constant term equal to 0. 1a squared, two numbers that multiply to -3 and add to +2. They are +3 and -1. Okay, see, at this point, like I said, either the numbers are small enough that you can really find that out. By the way, opposite, right? -3 or a equals 1. Or, we've done so many factoring problems that at this point it's really about the zero product property and even how we get into that quadratic. That's my larger focus with you right now. Okay, number 29. Completing the square. Okay, so we're kind of going back to the problems we were at before. I actually don't really see any difference between these and the other ones, so let's just keep working. Add 51 over, right? Completing the square, it's all about these two numbers here. So this will be x squared plus 6x plus some unknown number equals, I think that's 42, plus some unknown number there. Okay. Okay, 6 divided by 2 is 3. 3 squared is 9. So that's that. Now you have 42 plus 9. So there is a little bit of a difference in these problems compared to the ones in the beginning. I take that back here. What's different? Well, what's different is this answer we're going to kind of get. X plus 3 quantity squared is 51. Now we're going to take the square root of both sides here. And we're going to get x plus 3 equals plus or minus that square root of 51. Now, 51 is not a perfect square. So you have the ability to possibly simplify this radical, but you can't. This is an unsimplifiable radical. So we're just going to leave it like square root of 51. I mean, I'm not going to round the value. It's about 7 point something, but I'm going to leave it like that. Subtract 3, you'll get x equals -3 plus or minus the square root of 51. If you'd like to leave your answer like this, by all means, please do so. I'd like you to understand, though, that this is two separate answers. In fact, if we were talking about x-intercepts, because that's kind of what these things are when we get answers, this is how they'd appear. Like if this was a multiple choice test, your answers would be -3 plus the square root of 51, 0, and -3 minus the square root of 51, 0. If they rounded it, you can use your calculator and figure out what those numbers are. This number is a little more than 7 right here, so it's about -3 plus 7, so it's close to 4. And this number is close to, I guess, -10. But this answer, perfectly acceptable. Even written with the plus or minus, two different solutions merged as one, totally okay. Complete the square again. Let's go. 36. Get out of here. Plus 36 plus 36. V squared plus 12. Haha, you guys can help me complete, or plus 12v. Help me complete this square right here. -8 plus 36 is 28 plus that mystery number. What could it be? 12 divided by 2 is 6, and 6 squared is 36. Add 36 here, add 36 there. This reduces down to v plus 6 quantity squared. Again, it's that number, when you divide 12 by 2, it's actually this number inside here. It's kind of a nice little trick. 28 plus 36 is 64. Hey, good thing for us. That's a perfect square. Let's take the square root of both sides. V plus 6 equals plus or minus. See, the square root of 64 is 8. So plus or minus 8. So V equals -6 plus or minus 8. Do not leave your answer like this, because we can simplify this farther. We could not simplify this farther, as you can kind of see the difference there. So let's separate them. Either V is -6 plus 8, which is 2, or V equals -6 minus 8, which is -14. Okay, those are your answers. Now, I didn't mention this earlier, but I feel like I will right now. If a final answer, and assuming I did this work right, if a final answer results in an irrational value, something with a square root that you just can't take out, that means that the original problem was unfactorable had you written it in standard form. So if I added 9 this way instead and got x squared plus 6x plus 42, the simple and sad truth is that this is unfactorable. So if it's unfactorable, you must solve by completing the square or by quadratic formula. As this problem got us 2 rational answers, and look, they don't have to be integers. Your answer could have been 2/3. But as long as it gives you rational answers, that means that this problem written in standard form would have been factorable. What I mean by that is if I added 8 over instead and got v squared plus 12v minus 28, this is factorable here. It would have been 14 and negative 2, right? 14. So that is factorable. They asked to solve by completing the square. Looks like we still got same answer. Okay, solve with the quadratic formula. Okay, the quadratic formula is, how do you sing it? I don't have much of a singing effect. I don't have much of a voice right now. My voice is completely gone. But the formula itself is x equals negative b plus or minus the square root of b squared minus 4ac, all divided by the product 2 and a. This is true for any quadratic equation set up such as ax squared plus bx plus c equals 0. If this, then this. This is something where you can just plug in your coefficients into here. So that does mean as this thing here is written not in standard form, you have to get it in standard form. It must be written that way in order for you to use this formula. Otherwise, it simply does not work. So in order to do that, I'm going to have to subtract 4k over here and, get it in standard form. I did mention get into the habit of doing that for a good reason. 3k squared minus 4k minus 15 equals 0. Now, before you dive into quadratic formula, kind of 2 things here. Number 1, check and see if you have a common factor, because if you do, that saves you time for later when you might have to do something in the end with it. It looks like there are no common factors, which means these will be our 3 actual values. A is 3, B is negative 4, and C is negative 15. Number 2 is this. I would recommend that you substitute things into the discriminant first. The discriminant is this b squared minus 4ac, the guy that's inside the square root. There are multiple reasons as to why. I don't know if I'll dig into all of them unless they actually unless the reasons that I mentioned pop up. But one of the main reasons for right now is that, when you spend so much time rewriting this over and over and over as you're doing more computational work, most of the work that you have to do is inside here, right? And what do you have to do here? Switch this number sign? What do you have to do? Multiply this number by 2? In here, you have to square this, multiply these, subtract these, and take the square root. So why don't you kind of just do some of it to begin with first? Start with b squared minus 4ac. Again, it's called the discriminant. Now, there's a reason why that has nothing to do with what I talked about before, but the number has purpose. So let's try this. b squared minus 4ac. Negative 4 quantity squared is 16. This is 4 times 3 times negative 15. That is negative 180. We're going to do 16 minus negative 180. That's 16 plus 180, which is 196. That number inside the square root will be 196. So let's try and do quadratic formula now based on that. X equals minus b plus or minus the square root of b squared minus 4ac, see how quick that was, all divided by 2a. See, that way, when I go to my next step, everything's cleaned up as I need it to be. The opposite of negative 4 is positive 4. The square root of 196, lucky us, is 14. And 2 times 3 is 6. So x equals 4 plus or minus 14, all divided by 6. At this point, or even before that, you would want to split this up into 2 different equations. Let me just split it up right now. Either x equals 4 plus 14 over 6, or x equals 4 minus 14 over 6. If x is 4 plus 14 over 6, x is going to be 18/6, which is 3. But if x is 4 minus 14/6, that's negative 10 over 6, which can reduce to negative 5/3. Please don't write that as a negative 1.6 repeating kind of decimal, or please don't round it. Those would be your two answers there, 3 and negative 5/3 as well. Required standard form to begin with? Okay, that's fine. Okay, number 32, 12x squared equals negative 1. Let's go ahead and get this in standard form first. They did say quadratic formula. Let's add 1 plus 1 plus 1. 12x squared plus 1 equals 0. Now, as quadratic formula does have this b letter in it, you still need to have a value that represents b, despite the fact that it doesn't apparently exist in the problem. Oh, sure it does. It's 0x. We all know this. Let's put that in there. So we know that a is 12, b is 0, and c is 1. First thing I'm going to test here is the discriminant. That way I can get my value out pretty early. X equals, excuse me, I was about to do the formula. Discriminant, b squared minus 4ac. Let's check this out. 0 minus 48, negative 48. Now, here's another reason, and this gets into kind of the talk I was saying. This will idealize why you want to do the discriminant first. This is the number that goes inside the square root. This negative 48. If I did all this, blah, 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 this would be a negative 48 right there. Well, can we take the square root of negative 48? Not to get a real number, no, we can't. Try your calculator. It's going to give you an error. There's an issue. There's no real number that you can multiply by itself and get a negative result out of it. So I saved myself time from writing anything else in this quadratic formula. You know what happens when you get a negative discriminant, a negative inside the square root? We get to stop all work and write this simple answer. No real solution. No real solution. I'll just put no real solution. It's no real solution. There are no real numbers that we will get as a result of this stuff here. There are things called imaginary numbers and the complex number field. And no, I'm not making that up. You'll learn that stuff in Algebra 2. For the time being, when you get a negative solution inside your square root, inside your discriminant, understand that there will be no real solution. Now, I want you to understand something else here as well. In the previous problem, we had 16 plus 180. But remember, it was minus negative 180. You know how many times students accidentally forget this negative or this negative, and this turns into 16 minus 180, and you get negative 164, so you put no real solution? Be very, very, very careful about your work. That's why I talk about negatives. I say caution with those. Maybe do the things that some students do. They turn these into pluses after they count them, when they find out there's an even number of them. Just be very careful about what you do, because that's going to turn your answer into something wrong. Right? There's nothing wrong there. So again, how come I said the discriminant is a nicer way of doing this first? Well, one of those reasons really just comes down to the fact that this is all the work you have to do before you write your answer. Instead of plugging everything in before figuring out, I wrote all that just to figure out there's no answer. Yeah, it makes things a little smoother and quicker and easier. I think that's preferred. I think most people would agree. Sketch the graph of each linear inequality. Okay, so now we're getting into the greater thans or less thans of the world. To start with, what we're going to do is draw what's called a boundary line. The boundary line distinguishes between what our solution set will be and what our solution set will not be. And it comes in the form y equals 1/5 x minus 4. It's the same thing, but now equal to, in the sense that that's what the line is. Those xy values that are on the threshold itself. So let's start with that graph. 1/5 x minus 4. We start at 0, negative 4, and we rise 1 and run 5, just like we did on the previous graphs, and fall 1 and run 5 to the left as we maintain that positive slope there. Now, the one difference between this line And a normal line for y equals is because this is also not equal to, we are going to represent this with a broken dotted or dashed line, which basically means it is not a part of the solution set. It is not a part of the solution set. Okay. Okay, so we have a greater than symbol. We are comparing our y value to some expression that when we plug something in for x, we need to make sure that our y value is above it. So what side are we going to shade on here? Well, as long as we are on, in a y equals mx plus b, or y is mx plus b here, and we're comparing y to this thing here, it's a real simple method. It's called greater than, shade above the line. Less than, shade below the line. As this is a greater than, we will shade above. And don't worry, I'll double check with you. Let's shade above. It's going to look like that. And shade, and shade, and shade some more. That means any xy pair that I substitute into this inequality will give me a true result. For example, let's try 0, 0, because that really tends to work things pretty well, especially with x and with a fraction. Let's test 0, 0. That means 0 for y, 0 for x. If I substitute 0, 0, and the result becomes true, that means I shaded on the correct side. That means any other point here is a solution to this on this side, and any other point on the other side is not. 0 is greater than, what's a fifth of 0? 0. Minus 4, negative 4. Is 0 greater than negative 4? Oh, yes, it is. And because it is, it appears that I've shaded on the correct side of this here inequality. Okay? Okay, number 34, y is greater than negative x minus 2. Unfortunately, there's not much in the way of varying these types of problems. It's still a greater than, which means dotted line shade above. So let's just work with this graph here. It's like y equals negative x minus 2. So let's start at 0, negative 2, and let's, the slope here is negative 1, right? That's the number that's in front of x. Negative 1 over 1. So as I fall 1, I will run 1 to the right. Fall 1, run 1 to the right. See how negative slope works there? We're going down as we go to the right. And as we go up, we'd be going to the left to make that actually, work. So we'd be going like that. And these are the points that will help represent our boundary line. Okay, we're dotted there. And this time I'm going to make it blue, and it's going to look like this, broken. If you have trouble drawing broken lines, what you can do is draw your full line with a pencil, and then use the eraser, and kind of just make those marks, and that's fine. Okay, and let's go ahead and just fill it in. Greater than for y, shade above, right? So shade above, we got... Now some people get confused with shading above with shading to the right or left or something like that. No, no, no. It's not about shading to the right or left when you're comparing y with your variables, with your expression. What if you compare x, though? What if it was an x is greater than, which, by the way, I think I remember it pops up here somewhere. It might even be the next problem. Oh, okay, so what if it's an x is greater than? Yes, you're comparing right versus left. That's why, like I said, before you shade, probably try and test a point first, such as 0, 0. As long as 0, 0 is not on your boundary line, and as long as you know what side of the line it's on, it's a good number to test. Now keep in mind here, I'm testing 0, 0, and I'm expecting a true statement because of the side that I shaded on. If this was a false statement, then I've shaded on the wrong side. That's all it means. Okay, so 0 for y, 0 for x. Is 0 greater than negative 0 minus 2? Yes, this is true as well. I've shaded on the correct side as all these other ones will work. Nothing over here will give me a true statement. Only this side will. Awesome. Good shading. Okay, here's the x thing I was talking about. Sketch the graph of each inequality. X is greater than 4, x is greater than 0. Okay, this begins like the other ones here. You have to graph the boundary line like you would the equation x equals 4. Believe it or not, a lot of people have trouble interpreting what the heck this thing means. Some people see it as this. Some people see it as this. It's actually neither. X equals 4 is what, no matter what value y is, the value of x is going to be 4. Trying to think of it that way. Heck, try it like a table. Only this time in this table, plug in values for y, get values out for x. What if you plug in 0 for y? What do you get for x? You might ask, where do I plug in 0 for y? Well, I don't know, right? So what does x equal? Well, I guess 4. 1, 4, 2, 4, 3, 4, 4, 4, negative 1, 4. So all these values are 4. No matter what y is, x is 4. Up and down. So although we think of x as left and right, the graph goes up and down because it's going up and down the value of 4 for x. So it looks like this. I guess you just draw a vertical line at that point. Make it purple, vertical line straight up and down, and it is still dotted. You know, I don't know if any of our inequalities here will be a greater than or equal to or a less than or equal to. So while they're still kind of all the same, it's still good to know what all of them mean. Okay, do we shade above or below? Well, see, here you don't shade above or below. You can't. It's a vertical line. So because you're comparing x to 4 now, what are some numbers that you can try? We can test 0, 0 again. Here, let's test this before we even shade. Try this. 0, 0. 0 for y. Where do you plug in 0 for y? You don't. But 0 for x. 0 is greater than 4. That's not true. If 0, 0 doesn't give you a true statement, then no points on this side of the boundary line will give you a true statement. That means all the points on this side of the boundary line will give you a true statement. So as long as you are testing x values to this, you will be shading to the right as long as it's greater than. Greater than shading to the right. And forgive me for not coloring inside the lines here correctly. That's one of the things I failed in kindergarten. Guy knows how to simplify polynomial factors, but he doesn't know how to color inside the lines. Yeah, you know, it happens. Number 36, it seems kind of like a relatively easier problem than 35. They're kind of the same, but this one's right at 0. So you're going to graph the line x equals 0, which is the vertical line right here, right? No matter what y is, your x value is 0. Probably harder to kind of draw because you have to draw beyond the y-axis here. Thankfully, I have this color green. And look, I couldn't test 0, 0 at this point because 0, 0 is on the boundary line. So you could test 1, 0, something like that. As it's a greater than, we will still be shading to the right as well. So this problem remains the same. So I apologize for the lack of diversity for these problem types. Hopefully it's still kind of being covered in the same way. Understand the 0, 0 concept, the testing point concept, especially why 0, 0 is normally a pretty decent point to try. But like I said, in this problem here, it doesn't seem to really work out in our favor. But as long as you understand how you're comparing the variable to the expression on the other side, you'll probably know, and which variable it is, you'll probably know how to shade as well. It's 35 and 36 shading all done. Solve each system by elimination. Okay, so we're going back to some of the other stuff from before. You know, now we'll start playing with these problems a little more to ways of my liking, or just saying here's different things you can do, especially when the numbers get big. For example, I don't like these numbers. They're too big. I want to divide them by 4 because I can. C-A-N, I can. That's negative 5x minus 1y equals 7. I don't like these numbers either. They're too big. I'm going to divide them all by 2. How come? Because I can. And better yet, as I was saying this problem out loud to you, I really saw a pattern here. That, well, actually, I didn't see all of these. But check this out. Now when I add and play elimination, what happens? 0, 0, 0 equals 0. 0 equals 0. We've run into this before. What does that mean? Say it. Infinite number of solutions. Look, I'm done with the problem. There are a lot of other ways you could have manipulated them. They did ask you to use elimination in doing so. So you could have multiplied these by 2, right? That would have given you the same thing. But if you don't like the larger numbers, I personally don't care about the larger numbers, but I know a lot of people don't. But I'm also trying to go without the calculator as long as I can. So far, it seems to be working out. Okay, number 38 here. Can't divide by anything there, can't divide by anything there. So no making them smaller. Choose which variable you'd like to eliminate. There's an option of multiplying this whole top part by negative 9 so I can eliminate the y's. Maybe 16 times 9 is too big of a number for me. Maybe, hey, let's multiply this by 5. Right? I didn't change its sign. The number is smaller. You know, maybe it works out better for me. 2x times 5 is 10x. Y times 5 is 5y. Negative 16 times 5 is negative 80. Okay, number's still kind of big. Not as big as 16 times 9. 10x minus 10x is 0. 9y plus 5y is 14y. This equals negative 84. Divide by 14. This y equals, I think, negative 6. I think that's right. Y equals negative 6 when you divide by 14. Okay, we still have to solve for x here. Substitute this value in for y into an equation. Yeah, how about the top equation right here? Smaller numbers for sure. 2x plus negative 6 equals negative 16. 2x plus negative 6 is 2x minus 6. Let's add 6 to both sides. We'll get 2x equals negative 10, and x equals negative 5. All right. So x is negative 5, y is negative 6. Apparently that is where these two lines cross paths, at negative 5, comma, negative 6. And as long as I get integer answers, I think I'll trust that the work is right. If it's a fraction, maybe I'll question it a little bit. Solve your system by substitution. Okay, so this goes back to that equal values method stuff we talked about. The problems here aren't necessarily getting harder. They're just different. In fact, these are the last two before we do our sequence stuff. So we've actually finished everything else outside of sequences. So if y equals this and y equals that, then this equals that, right? Substitution. Substituting the expressions in for y. Okay, you know, when I was saying that sometimes I like to err to the side of x as being positive, even if that means moving the values to the right. Maybe you didn't see that part of the video, or maybe you didn't hear it, but what if I want to add 3x to this side? That's okay. And then I guess I subtract 1 over here, right? So subtract 1. And remember, and don't forget this negative 9, by the way. You know, I know that those negative symbols get lost a lot as well, especially after crossing out. You just tend to see the number that's there, and anyway. So this is a negative 10, this is a positive 5x. Now, I divide by 5 internally, mentally in my head, and I see that x is negative 2. So I write x is negative 2. And then I get the hand raised. Mr. Robinson, how did the x go over here? Well, you can switch sides of an equation. It's called the commutative property of inequality. If a equals b, then b equals a. So you can rewrite them. I tend to skip those steps here and there. So I say them out loud, and I hope it pans out. Okay, y equals negative 2x plus 3, and y equals 3x minus 7. Once again, equal values method. If y equals this can take place of y there. So we'll get negative 2x plus 3 equals 3x minus 7. Kind of same exact thing as last time. In fact, it's almost the same exact answer. Let's switch and skip the color stuff. Add 2x, add 2x. Add 7, add 7. We get 5x equals 10. Divide by 5, x equals 2. You know what? I didn't finish this problem. I'm sorry. I was starting to say these problems seem a little short. I'm sorry. So on number 39, x equals negative 2, you got to solve for y. See, I wouldn't have even gotten 100% in my own test. Would have missed out. Substitute negative 2 for x somewhere, like, right here. Y equals 2 times negative 2 plus 1, which is negative 4 plus 1, which is negative 3. So we have a solution set there that's negative 2, negative 3. I think this was one of our answers earlier in a previous problem. Sorry, I'm kind of interested in seeing if this was the exact same problem. Let me check this out. Let me go back a little bit. Look for a negative 2, negative 3 somewhere. That just rings a bell. Maybe it, oh, it's 2, negative 3. See, that is, because I saw this, that looks familiar. So, totally different equation, though. Totally different problem, right? So, okay, we're back. Sorry about that. Tickled my fancy a little bit. Negative 2, negative 3. This one, x equals 2, substitute that into an equation and solve for y. Let's use the bottom one. Okay, y equals 3 times 2 minus 7, which is 6 minus 7, which is negative 1. So y is negative 1, x is 2, or your solution set is 2, comma, negative 1. Ordered pair is the final answer for both of these. Don't just stop on x, please. I think I was really catching the breeze there. I said, oh, this stuff's a lot easier again. Okay, on to sequences. I don't know why I had this title other than letting you know this is kind of the next part. These questions go 1 through 12. They're not 41 to 52. That's part of it. But all this is devoted to sequences, arithmetic and geometric. Try and keep it short. Determine if the sequence is arithmetic. If it is, write and the formula. Okay, I think it's write the formula. Write the formula and find the 52nd term. Okay, so let's write the formula and find the 52nd term. If it's arithmetic, that's all they're asking. If it's not arithmetic, guess what? They're not asking us to write anything. And guess what? Neither will I. I'm not going to do it if it's not. Because I assume when we get into the geometric stuff, we'll go on from there. Okay, to begin with, a sequence is a list of numbers. This list of numbers will have a certain pattern with it. In an arithmetic sequence, the pattern is that they share a common difference. A difference is a matter of subtracting one number from another. 54 minus 24, we have to see if that's the same thing as 84 minus 54, or 114 minus 84. Now, I think people tend to not say it that way. I think they say 24 plus what number is 54, which is fine. When we get into the ratio part, you'll see why the thing that I said is probably more important. These are all plus 30. And assuming these are plus 30, we have to assume that the rest of the pattern stays the same at this point. If this was 30 and this was 30, maybe make sure this one isn't 31. Okay, but it's not, it's 30. So this one is an arithmetic sequence because between the terms, they share a common difference of the number 30. Now, D is the letter that denotes the common difference in itself. D is the number 30. And it's a positive 30. We add 30 to go from one term to the next. As far as the arithmetic sequence goes, the formula is kind of written like this here. T sub n equals D times n plus T sub 0. You might also see it as T of n equals D times n plus T of 0. Or A sub n equals D times n plus A sub 0. You might see one or the other. You might see it also expressed as a first term order, meaning using T sub 1. I will not be doing that for arithmetic sequences. I prefer this as it relates a lot to y equals mx plus b. And the other way still cleans up to that anyway. Finding term 0 for common difference problems normally isn't that much of an issue. For geometric series, sometimes it is. But the whole point here is that we need to write an equation that says T of n equals, we're going to use our common difference here. It's going to be multiplied by n, and we're going to be adding term 0 here. So we needed our common difference D. We got that. We need to figure out what term number 0 is. And term number 0 is not an actual number in the sequence. It's a theoretical one that helps explain how many times we add our common difference to get our next number. If we subtract 30 from 24, we're going to get negative 6. Term 0, the value of term 0 is negative 6. So 30n plus negative 6 is 30n minus 6. What this thing means here, and this is the equation, this isn't probably the best way to write it in terms of telling the story. I'd say the better way of telling the story actually is to write the negative 6 first, even though it's not as mx plus b order. What this means here is that if I want to find the value of a term, say term 100, say term 52, right? We have to find the 52nd term. Let's do that. Find the 52nd term. N represents the term position, the term number, like the 52nd term. T of n represents the value of that term. So the value of the 52nd term is negative 6 plus 30 times 52, or you can do it here as well. But what this story tells you is that starting from the number negative 6, which by the way is not your first term, right? It's term 0. Starting from the number negative 6, I could tell you what a term number is by adding 30 that number of times. If I want to find term 1, I'm going to add 30 once from negative 6. If I want to find term number 4, I'm going to add 30. 1, 2, 3. 4 times, right? This first one is a plus 30. Here's negative 6. If I want to find term 52, I'm going to add 30 52 times. Now there's a very, very easy way of adding 30 52 times, doing 30 times 52. 30 times 50, because I'm not using the calculator, 30 times 50 is 1,500. So 30 times 52 is 1,560. 1560. 1560 minus 6 is 1554. We found the 52nd term of this list here by adding 30 52 times from this number. Okay, see how term 1 doesn't work the same? Because if I want to find term number 2, how many times would I add 30? Just once. Term number 3, add 30 twice. So if we want the number to match the term number, then we need a term 0 to make that happen. We just did. So term 52 is 1,554. Here's the general equation for that. Okay, I'll do the same thing here. What we're trying to determine is what the difference is between each number, meaning what we have to add to go from one term to the next. Looks like we have to add a negative 3, so subtracting 3 here, subtracting 3 here, and subtracting 3 here. Okay, it appears that it has a common difference of negative 3, which means this is an arithmetic sequence. So I will write the formula. We have our common difference. We do need the value of term number 0 by subtracting negative 3, which is adding 3. Adding 3, figure out what term 0 was. Negative 19. So the value of term 0 is negative 19, which again does that same explanation as before. In order to find the value of a very specific term number n, I will start from the number negative 19, and then I will add negative 3, so subtract 3, n times to make that happen. So your equation is t of n equals negative 3n minus 19. Again, it's like y equals negative 3x minus 19. That's the same thing. Sequences have this idea, though, if we graphed them, they are discontinuous, meaning they only have values at these terms. There's no such thing as term number 0.5 or term number negative 7. Even ideally, term number 0 really shouldn't exist. Your list does start right here. But in order for us to find any other term, like say term 52, we are going to use that negative 19 in aid of trying to determine what the value is, because we're going to subtract 3 52 times. Negative 3 times 52 is negative 156. Gee, we can't get away from that 156, can we? Minus 19 is negative 175. So the value of term number 52 is 175. And please don't ask me where we're going to use this kind of stuff in the real world. I mean, you know, this common sense stuff I think is just as important as anything else. I'm not saying, well, say you had these people. No. There are applications to this in the real world as there are in math and everything else as well. The point is, are you able to accomplish what it is that you are? Can you make sense of what's there? And can you show that to us? I think that's the biggest feature here. Okay, there's some more. 2 more. Determine if they're arithmetic, arithmetic, and if it is. I am going to presume here that these are all arithmetic. Otherwise they probably wouldn't put them here. So it looks like I am subtracting 20 each time here. Minus 20, minus 20, minus 20. So it is arithmetic. It does have a common difference of negative 20. And again, if you really do want to see what those numbers are, because I think I jump into geometric next and I'll have to talk about it, what I'm doing is I'm taking this number and subtracting this number to find the difference. Negative 14 minus 16, or excuse me, minus 6. And then we're doing negative 34. Are we doing minus 14? No, we're doing minus negative 14. Negative 34 plus 14 is negative 20. And then negative 54 minus negative 34. Negative 20. So that's what's happening. We're subtracting a lead term from the trailing term, the value. Okay, common difference is that if we subtract 20 going to the right, then we add 20 going to the left. For term number 0, 6 plus 20 is 26. So term number 0 is 26. And away we go. T of n equals negative 20 times n plus 26. 52nd term. Let's look for it. T of 52. And, none of these problems really change what it is that you're doing. It seems like it's the same kind of process. Process is important, but, understanding what you're doing equally as important here. And, hey, what I'm doing right now for myself, I'm working on my mental math, like negative 20 times 52. Well, 2 times 52 is 104, so add a 0, it's negative 1040 plus 26. The calculator is not required. We'll see if the geometric sequence requires calculators. We'll see. Looks like this is negative 1014, negative 1014. It should make sense that the numbers are getting farther negative for the 52nd term as they get very large. So as long as your answer doesn't become positive, maybe there's a reason to trust it. I don't know why this keeps saying right and the formula. I'm sorry. Number 4, common difference. Well, you know what I'm kind of doing for some of these, because I sometimes have trouble. This minus what gives me that? I look at these ones first sometimes. Hey, this is minus 200. And as long as you look hard enough, yes, this is 3 minus 200 is negative 197. You have $3, you pay someone 200, you're out 197, I guess? Sure. So common difference is negative 200, so it is an arithmetic sequence once again. And I'm going to add 200 as I subtracted 200 the other way to get term number 0. So term number 0 is 203. I'm not sure if I'm going to be fanatical about finding term 52. Actually, common difference of 200 isn't too bad. But T of n equals negative 200 times n plus 203. Again, starting from the value 203, subtracting 200, n times gives you the value of term number n. So let's find the value of term 52. That'll be negative 200 times 52 plus 203. Actually, no, this won't be too bad. What did we say before? 52 times 2 is 104. So this is negative 104, 00, plus 203. Negative 10,400 plus 200 is negative 10,200. Plus a 3, that's negative 10,197. Remember, it's getting closer to negative 10,000, not farther. So it looks like it's that number there. I mean, look, the last thing anyone's expecting you to do is actually subtract 52 200 times, even if it was in your calculator. Use multiplication as it's supposed to be used, as a way of saying how many times you add something. And I'm really mentioning that because right now when we go into geometric sequences, it's important to know how exponentiation works. Determine if the sequence is geometric. If it is, find the common ratio, the 8th term, and the formula. All right, well, the formula will require the common ratio, so I know I'm going to be finding this anyway. I'll probably be finding the formula before I find the 8th term. Note that these numbers are probably short enough to keep multiplying by that thing to find it. I understand that. But I want you to know it both ways, I guess. Okay, a geometric sequence is, another type of sequence, a listed number separated by some sort of frequent pattern. In a geometric sequence, the difference is some sort of ratio, some sort of multiplication. Okay, so the question is not what number do I add from here to there and here to there and whatever. The question now is what number do I multiply by? And I know that you know what the answer is for this one and probably for problem number 6 as you look at it. I'm hoping that in due time I could either come up with one or that they will come up with a number that is so ridiculously hard to do, not because it's big, maybe because it's a fraction, that it's harder to determine what it is you're multiplying by, so you can hear me out when I say this. As we know that the answer is times 2, we get our 2 by dividing a lead term by its trailing term. Your common ratio is 2 because negative 8 divided by negative 4 is 2, and negative 16 divided by negative 8 is 2, and negative 32 divided by negative 16 is 2. That gives you this common ratio. Okay. If the numbers were too hard to determine what to multiply by, always do this division to figure it out. That's why I'm saying this right now. I really want you to hear that out loud. Now, all this being said, your numbers are getting farther negative, and that's okay. that doesn't make your ratio -2 here. Negative times a positive is still a negative. Okay, in this case, you have two different formulas to work with. They're both kind of the same thing, but it depends on what term you start on. There's starting from term number 0 and multiplying by your common ratio exactly n times, kind of just like the previous one with the arithmetic sequence, starting from term 0, adding your common difference n times. Or starting from term number 1, and trust me, I know I'm going to have to explain this a little bit, and multiply it by your common ratio 1 less time than your term number itself. Okay, for this first problem, I'm just going to use this one here because I think it makes sense to you what it says, and because it's going to be a simple term 0 to find. -4 times 2, blah, 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 blah. To go the other way, to find term 0, we're going to have to divide by 2. Divide by 2. Same as multiplying by 1/2. So your term 0 is -2. Your term 0 is -2. So as long as that number is a clean one, it's probably the best way to write the equation in this form right here. T of n equals -2 times, and I really like to put this in parentheses if I can, +2 to the n power. Now, I'm not going to clean this up into -4. If you know order of operations, then you know you have to do this number first here, the 2 squared, 2 to the n power. And -2 either comes last or technically can come first, but make sure this is married together before calling this -4. So, let's find term number 8. There's a conventional way of doing it, which is, here's the first term, second, third, fourth. What's the fifth term? Times 2. That's 64. -64. Times 2. -128. Times 2. -256. Times 2. -512. Now, if you have a calculator, it's probably no problem. As long as you know how to count right, and you multiply by 2 correctly, and you remember your negative, you'll get that answer. The value of term 8 is -512. But as long as you have the equation set in stone, this shouldn't be much of a hassle either. If we're going to find the value of term 8, we're going to substitute 8 in for n. Now, I'm going to start from -2 and multiply by 2 n times, 8 times in this case. And of course, I guess at this point, you kind of have to use the calculator as well, right? Let's see, 2 to the 6th is 64, 7, 120. So it's 256. So -2 times 256, which looks like it's -512. So there's the answer. So remember, I do 2 to the 8th first here. Now see if this makes sense with this number. -2 is term 0, not an actual term in the sequence, but it helps me understand that to find the value of term 1, I have to multiply by 2 once. And term 2, I have to multiply by 2 twice. And term 8, 1, 2, 3, 4, 5, 6, 7, 8. So it looks like, that's exactly what happened here. So I multiplied by 8 times. Now, why do I use this one? Well, I'm going to use this one in some instances, like problem number 6. And look, I can use this one still. You just might not appreciate using this one for problem number 6. What's different with problem number 6? Well, it is geometric because it looks like it has a common ratio of -2 this time. Notice how the signs change. Common ratio of -2. But that's not the main thing I want to talk about. The main thing I want to talk about is term 0. What is the value of term 0 here? Well, we divide 3 by -2. So you can either write it as -3/2 or -1.5. It's up to you. Most people would prefer not dealing in terms of this right here, especially if they have to find another term after that. Or if this number was too hard to find in itself because of a tough common ratio and a tough term number 1 to begin with. This one happens to be okay, but it's not an integer. How about we just stick with term number 1 this time? How about instead of term 0, we speak on term 1 and we use this formula here. So term 1 is 3. So we're going to use T of n equals 3 times your common ratio of -2 raised to the n minus 1 power. Okay. Now this one looks a little more strange here because of this. And not only that, if I explained it to you, hear this explanation again. I start from this term here and I multiply by 2 this number of times to get that, for the value of term n, I start from -2 and I multiply by 2 n times. to find the value of term n here, I start from 3 and I multiply by negative 2 n minus 1 times. Right? To find the value of some term, I have to multiply by negative 2 one time less than the term number itself. Sounds a little bizarre, but let's see if it makes sense. We got to find term 8, right? Okay. Well, here's term 1, 2, 3, 4. Let's find 5. Whoops, positive 48. 6. Negative 96. 7. Negative, positive 192. And 8. Negative 384. So term 8 is 384. Negative. Okay, let's see how that worked out. Starting from term number 1, how many times will I have to multiply by negative 2 to get to term number 8? Remember, I don't count this number. I count these. 1, 2, 3, 4, 5, 6, 7. If I'm going from term 1 to term 8, I'm only doing it 7 times. If I go from term 0 to term 8, I do it 8 times. So if I want to find the value of term 1000, I'm going to start from term 1 and multiply by negative 2 999 times. 1 time less than the term number itself. That's how this thing makes sense. Could have I started from negative 3 halves and multiplied by negative 2 8 times? Absolutely. And I could have written that equation as well. Some people just don't like dealing with fractions if they don't want it to exist. But let's do this in the conventional, I guess the other way is conventional, in the mathematical way here, substituting. Notice, start from 3, multiply by negative 2 7 times, and 2 to the 7, negative 2 to the 7th is negative 128, so we're going to get this answer here, negative 384 for the 8th term. Common ratio, we answered way up here. It was like the first thing we found for both of these here. All right, so we got our equations there and our values there. All right, we got 2 more sets of these. Doesn't look like they're straying too far away from what we last did. Okay, that's not too big of an issue, I hope. And I hope you can recognize here as well what your common ratio is, negative 2. You think term 0 is okay to find in this one? Divide by negative 2? Yeah, I think it's fine. Let's go and find term 0 this time. 2 divided by negative 2 would be negative 1, so there's term 0. So the value of any term can be found by starting from term number 1 and multiplying by your common ratio exactly n times. Okay? Again, don't merge these. Let's find the value of term 8 just this way. Negative 1 times negative 2. Whoops. Negative 2 to the 8th power. Okay. Negative 2 to the 8th power, all these negative base raised to an even power will be left with a positive number. Negative 2 to the 8th is positive 256. So negative 1 times 256 is negative 256. That's the value of term 8, and there's your equation right there. So again, kind of just doing the work, drawing the arrows, doing something like that. Whatever it is that helps you find it is going to be your best medicine here. Okay, number 8. Common ratio. I think you see it. What, negative 3? Negative 3? Yeah. Okay, to find out term 0, let's divide by negative 3. Negative 2/3, I guess. No, let's not deal with the fraction. Let's do term number 1. I don't like fractions. You don't like fractions. Look, the thing is, like I said, you could write this down just fine, but then you have to calculate with it. And I don't want you to get lost in order of operations either. Let's just leave with term 1. And the value of any term can be found by starting from term 1 as long as you just multiply by 3 one less time than the term number you're looking for. Term number 52, we'd multiply by negative 3 51 times. Term number 8, we'd multiply by negative 3 7 times. 2 times negative 3, 7 times. Negative 3 to the 7th, actually, to be honest, I don't know that one. 3 squared cubes, don't make me use the calculator. 4th, 5th, 729. 729 times 3. 729 times 3. 87. Is it 2187? So 2 times negative 2187. I'm going to double check this in the calculator in the end. because I don't want to write the wrong answer. Negative 4, 3, 7, 4. Term number 8. I'm going to see if that's right. Here we go. I got 2 times negative 3 to the 7th power, negative 4 through 7, 4. All right. See, mental math is still fun. That's the value of the 8th term. Here's the equation itself. I think I'm done on those parts. Now, find the missing term or terms in each arithmetic sequence. Okay. The fact that you know it's arithmetic means that you know there's a common difference. Now, there is a guess and check way of solving these, meaning try and add something twice until you find out what the number is. But there's also an algebraic way of doing this. As this is an algebra class, you could say, hey, I'm adding some common difference here of which I am unsure what it is. Let's call it D. If I take negative 37 and add D twice, apparently I get negative 17. So what is D? Solve for it like you would for X, for anything. Combine like terms. Add 37 to both sides. I think that number is 20. And then divide by 2. D is 10. So D is 10. That's awesome. That helps us find our missing term. If the common difference is 10, then these become a 10, and a 10. Negative 37 plus 10 is negative 27, plus 10 is negative 17. Now, do you think you could argue in your best case scenario that you could have found that number more quickly than I could have? Absolutely. Oh, totally. I think I saw that answer before as well. In a worst case scenario, though, you want to make sure that you have a fallback plan that'll take equal amount of time no matter what the answer is going to be. For example, I think here we can all agree that this number is going to be negative 24. Okay, but for the sake of practice, I think it's really important for you to understand what it is that you're doing here. In fact, even when you're doing the algebra, I think it's almost as important that you understand what it is we're doing there as well. Just because you do the algebra might not mean that you understand the logic behind what's happening. So let me try and explain it in this one. You're adding some number twice to go from negative 26 to negative 22. You're going to figure out what half that value is so that you can then go halfway in between. What number are you going halfway in between? The distance from negative 26 to negative 22. This full distance is 4. That's when we add 26 to both sides here. The full distance is 4. We need half the distance. That's when we divide by 2. So the D value is 2. Half of 4 is 2. That adding 2 this way or subtracting 2 this way gives us negative 24. Okay? Arithmetic. And these two are arithmetic as well, apparently. So these are the last two problems of this entire video. I am done after this one. We are wrapping this up. In all honesty, I think we made good time, all told, with 52 minutes. But hey, let's do this again really quickly here. I think there's not really much to say about these problems anymore. Now we've seen them. I think what I do want to do, though, is tell you about what would happen with geometric sequences. Okay, so after we solve these two, I just want to lightly touch upon, I can even give you an example, but lightly touch upon how you deal with geometric sequences, because even if you understand what it is you're supposed to do, you might not know how to maybe use the calculator for it or anything else like that. Anyway, I hope you trust the math that I'm doing here. Combine like terms, subtract 18, divide by 2. D value is 3, add 3, you get 21. That seems to work out. But anyway, as I'm talking through these problems, because they're kind of the same thing over and over, as I'm talking through these problems, I'd love for you to hear me out about geometric sequences. Geometric sequences are separated by multiplication. Okay? That means that you're trying to find some value that when you multiply by a common ratio a certain number of times, you have discovered it's called a geometric mean, but the missing term in between there. And in order to find out that number, understand you're going to have to multiply by your common ratio twice, which means you're going to square it. Okay, you're going to square it. So that requires taking the square root. So I'll try one or two problems with you right after this. It's going to be pretty quick here. Check this out. Your common difference here is negative 9. That means we're subtracting 9. So negative 23 minus 9 is negative 32. See, negative 23 plus 9 would have been negative 14. That would have went the wrong way. This seems to be going the right way here. Okay, I do understand that we're done with this whole thing. Let me just give you just two other problems here in the very end. They're two bonus problems. Let's call them 13 and 14. Okay, let's start with with an easier one here. Maybe one that you probably wouldn't notice right off the bat. But 6, and then some number, and let's call it 54. Okay, this is geometric, which means common ratio. Okay, we're going to multiply 6 by some number and multiply that by some number. I'm using the letter R for common ratio. So 6 times some number is 54. Well, R times R is R squared, so 6R squared equals 54. Interesting. How do you solve? 6 times R squared. Remember, this is 6 times R squared. So you divide by 6. Divide by 6. That's R squared equals 9. And R, take the square root. What's R? Guess what? It's not just 3. It's plus or minus 3. The square root of R squared is plus or minus 3. Does that actually work? Well, 3, I think we can assume works. 6 times 3 is 18. And yeah, 18 times 3 is 54. But did you know that 6 times negative 3 is negative 18? And negative 18 times negative 3 is positive 54 as well? So guess what? There's more than one common ratio here, and there's more than one answer here. There are two of them. So even if you use guess and check, I doubt you would have found the other one in that geometric sequence. Once again, this process is kind of a nice one to know about when something like that falls into play. Right. Okay, let's try another one. I guess a little trickier. Let's start with negative 2. And I'm going to add 2 blanks this time to kind of help you out with, how you just how you figure these things out, right? Let's go to negative 128. Okay, so instead of trying the phone book to figure out what the answer is, and look, I could have made it harder for you and made fraction answers. This shouldn't be a fraction answer. Understand how many times you're multiplying by your common ratio to get there. It looks like 3 times. Negative 2 times R times R times R equals negative 128. Negative 2 times R cubed equals negative 128. Guess what? We're not going to be dealing with cubics, I don't think, really much on this final. But divide by negative 2, R cubed, negative 128 divided by negative 2 is positive 64. I guess one thing I could mention here is that when you take the cube root of both numbers, which taking the cube root you can do on your calculator there, taking the cube root of a number is not plus or minus. It's just the sign that you have. For example, cube root of 64 is positive 4. It's not plus or minus 4. If you're uncertain why, you want to know what negative 4 cubed is? Negative 4 times negative 4 times negative 4. That'd be negative 64. So you can take the cube root of negative numbers, and you can take the cube root of positive numbers. There is no plus or minus split. It's just 4. So negative 2 times 4 is negative 8. Negative 8 times 4 is negative 32, and apparently negative 32 times 4 is negative 128. So those are just ways of doing all those problems there. We have done an entire final review here. A couple hours here, a few hours, getting through 52 total problems. A lot of different ways to attack them, a lot of common mistakes that you saw along the way. If you want to look all the way back at what we did, I'm going to do some rewinding right now, and I'll just talk through this. We did a lot on quadratics, a lot on factoring at the quadratics, completing the square. Only 2 quadratic formula problems, but we looked at discriminant. We looked at no real solution cases. We did linear systems of linear equations and word problems. We did linear inequalities as we worked on that. We did sequences, okay? We did exponential functions and graphing and worked with them with arithmetic and with geometric sequences with the graphs there. So we did a lot of different problems here, spelling out processes for these word problems here, trying a lot of different ways what infinite number of solutions, no solution looks like. Whew, this is a whole lot of stuff being done here, and I sure hope that it helped you. It got me kind of in that right mood, and I'm very happy to have done this thing for you. So as I jump all the way back to the end, once again I say, ask me questions at any time, please, if you have them. Okay, I'm always here to help you on that, and always help find those missing terms in your soul. I don't really know how to end this else other than to say, Fiend!